Far beyond Pluto, past the scattered rocks of the Kuiper Belt, lies a place so distant and faint that no telescope has ever really seen it. Scientists believe there's a huge, invisible halo of frozen debris surrounding our Sun, carrying secrets from the very birth of the solar system. They call it the Oort Cloud. But what if it's more than just a cloud of ancient ice? What if it's the true edge of space as we know it, a kind of border between our familiar solar system and the endless unknown beyond? Before we uncover what could truly exist at the edge of the Oort Cloud, drop a comment below and tell us where in the world you're watching from and what time it is now. Now settle in and enjoy a fascinating journey through space. In the year 1950, a Dutch astronomer named Jan Oort proposed an idea so daring that it would change forever the way humanity thinks about the far reaches of our solar system. He suggested that beyond all the planets we know, even farther than the distant and icy dwarf planet Pluto, there exists a vast, invisible cloud made of countless icy objects. This was not a wild fantasy, nor a mere guess made from speculation. It was a carefully reasoned conclusion, drawn from decades, indeed centuries, of observations and meticulous study of one of the solar system's most mysterious visitors, the comet. For as long as human beings have gazed up at the night sky, comets have fascinated and perplexed them. These brilliant travellers would suddenly appear in the darkness, blazing across the heavens with luminous tails that could stretch across vast swathes of the sky. One night they might astonish, and the next vanish entirely, leaving observers to wonder where they had gone. Sometimes comets returned after many years, decades, or even centuries. Other times they never returned at all. They were, in the truest sense, enigmatic wanderers, appearing as if from nowhere and vanishing just as quickly. For generations, astronomers carefully recorded the movements of these celestial visitors. They plotted their paths, noting every twist and turn, every appearance and disappearance with increasing precision as telescopes became more powerful. By the mid-19th century, there was enough data to see a pattern, one that had been hidden in plain sight for centuries but had eluded understanding. The pattern lay not in the comets that visited frequently, but in a special class of comets called long-period comets. These were comets that did not return every few years or decades, like Halley's Comet, but rather took hundreds of thousands, sometimes even millions of years to complete a single orbit around the Sun. The key clue came from observing the furthest points in these cometary orbits, known as aphelia. Unlike the planets, whose paths were well understood and confined, many of these long-period comets had aphelia at incredible distances, far beyond anything previously mapped in the solar system. More puzzling still, they seemed to arrive at the inner solar system from all directions, completely randomly. Some came from above the plane of the planets, others from below, and yet others from nearly perpendicular angles. This randomness was a profound mystery. If comets came from a flat, disc-shaped region beyond Neptune, as the planetary system itself seemed to be arranged, then they should have entered the inner solar system along roughly the same plane as the planets. The fact that they did not suggested something entirely new. These comets were not coming from a flat disk, but from a spherical reservoir surrounding the Sun. In other words, the comets were likely being stored in a three-dimensional structure, a halo of icy bodies enveloping the solar system like a faint, invisible cocoon. Jan Oort began to examine the mathematics of these cometary orbits. He considered the effects of gravity, both from the Sun and from passing stars, and the tiny perturbations caused by collisions or near misses with other objects. If these comets had been making their journeys for billions of years, he reasoned, their orbits would have been altered over time. They would appear worn, disturbed, and ragged from countless encounters over eons. Yet, curiously, the comets he studied looked almost pristine, fresh, as though they were entering the inner solar system for the very first time. This realization led Oort to a groundbreaking conclusion. If these comets were indeed on their first inward journey, they must have been stored far away, untouched and preserved for billions of years. Something somehow had nudged them from their distant resting places, sending them on their long journeys toward the Sun. The concept he formulated was as elegant as it was audacious. Somewhere beyond the planets, at distances almost impossible to imagine, there exists a gigantic cloud of icy objects quietly orbiting the Sun, waiting for the rare gravitational disturbances that might send them hurtling inward. Oort estimated that this cloud began tens of thousands of times farther from the Sun than Earth is, stretching almost a quarter of the distance to the nearest star. To put that in perspective, the distance from the Sun to Earth is about 150 million kilometres, or roughly 93 million miles. Multiply that by tens of thousands, and the scale of this proposed structure becomes almost incomprehensible. It was not a neat, tight ring or disk like Saturn's rings or the asteroid belt, which are confined to relatively narrow planes. Instead, Oort imagined it as a loose diffuse sphere, a three-dimensional shell of icy debris with each object separated from its neighbours by millions of kilometres, all slowly circling the Sun in a frozen cosmic dance. This idea elegantly solved several long-standing puzzles about comets. First, it explained why comets could still shine so brightly, despite their ancient age, and why they could carry so much ice even after billions of years. The secret was that they had spent most of their time in the dark, frozen outskirts of the solar system, far from the Sun's heat. Only occasionally, when gravitational nudges sent them inward, did they experience the fiery warmth that created the glowing tails visible from Earth. Second, it explained why their paths seemed so random. If comets emerged from a spherical cloud rather than a flat disk, then it made perfect sense that they could approach the inner solar system from any direction. Oort was not the first astronomer to suggest the existence of such a cloud. In the 1930s, an Estonian astronomer named Ernst Üppig had also proposed that comets might originate from a distant, unseen reservoir. However, Üppig did not develop the idea in detail, nor did he provide the precise mathematical reasoning to support it. It was Oort who rigorously analysed the comet data, applied the mathematics of orbital mechanics, and provided estimations of the distances involved. For this reason, the concept eventually became known as the Oort Cloud, though some astronomers choose to honour both men by calling it the Üppig-Oort Cloud. At the time, Oort's proposal was remarkably bold. It required imagining a structure that could not be directly observed, stretching across unimaginable distances, composed of objects so small and dim that even our most powerful telescopes today cannot see them. More than 70 years later, astronomers still have no direct images of a single object from the Oort Cloud, yet its existence is continually confirmed indirectly. Each time a new long-period comet is discovered, its orbit is traced backward, and every single time, the path points toward that distant spherical reservoir Oort had predicted. Oort's idea was revolutionary not only because it explained the strange behaviour of comets, but also because it expanded the known boundaries of the solar system. Before his insight, the solar system was widely assumed to end with Pluto, a frozen little world orbiting at the edge of the known planetary family. Beyond Pluto, most astronomers imagined empty, lifeless space stretching endlessly into the cosmos. Oort's theory shattered that notion. It revealed that the Sun's gravitational influence extends far beyond the furthest planets, capable of holding on to icy fragments on the very threshold of interstellar space. In other words, the solar system is far larger and more complex than anyone had imagined. This new perspective opened countless questions and possibilities. Could the Oort Cloud contain material from the very formation of the solar system, remnants left over from the swirling disk of gas and dust that formed the planets? Might some of these icy fragments even predate the Sun itself, captured long ago from neighbouring stars in the galaxy? Could disturbances from passing stars or the tidal forces of the Milky Way galaxy send waves of comets inward, potentially explaining periods of heavy impacts on Earth in the geological record? The Oort Cloud also invites reflection on the nature of time and preservation in the cosmos. While comets in the inner solar system are exposed to sunlight and heat, gradually losing their volatile ices, the objects in the Oort Cloud remain frozen, unchanged for billions of years. They are a frozen library of the early solar system, untouched by the processes that have altered the planets and asteroids closer to the Sun. Each comet that journeys inward carries with it a story from the dawn of our solar system, offering clues about its formation, composition, and evolution. Despite the distance and darkness, the cloud influences the inner solar system in subtle ways. Occasionally, a gravitational nudge, A passing star, a rogue planet, or even tidal forces from the Milky Way itself sends a comet spiraling inward. These events are rare, but they provide spectacular shows for observers on Earth and offer critical data for astronomers seeking to understand the hidden structure of our solar system. Each new comet is like a messenger, travelling across tens or hundreds of thousands of astronomical units, bearing secrets from a region that can never be seen directly. Jan Oort himself never observed the cloud that now bears his name. He did not point a telescope at a faint speck in the distance and see the icy objects drifting in the darkness. Instead, he achieved something far more remarkable. By carefully studying the paths of comets across the sky, he was able to infer the existence of an entire hidden realm. His work reminds us that astronomy is not only about what we can see directly, but also about what we can deduce from subtle patterns, mathematical reasoning, and a deep understanding of the forces shaping the cosmos. The discovery of the Oort Cloud also transformed the way scientists think about the solar system's structure and history. It suggests that the solar system is not just a simple arrangement of planets orbiting a star, but a dynamic, multi-layered system, with regions so remote and silent that they remain invisible even to our most advanced instruments. The Oort Cloud, as a spherical shell of ancient icy bodies, provides a bridge between the familiar planets and the vast, unknown interstellar medium beyond. It is humbling to realize that the solar system extends so far. While Earth orbits a comfortable 93 million miles from the Sun, the Oort Cloud may begin tens of thousands of times farther away, stretching toward the nearest star. This is a distance almost impossible for the human mind to comprehend, and yet the gravitational pull of the Sun remains strong enough at those remote distances to hold countless icy fragments in orbit, patiently waiting for the rare moments when they might journey inward to reveal themselves. Oort's vision was not only scientific but also profoundly imaginative. He challenged the limits of what astronomers could infer, combining careful observation with bold speculation. His work exemplifies a key aspect of astronomy, the ability to see beyond what is directly visible, to imagine structures and processes that are inferred rather than observed. In this sense, the Oort Cloud is both a scientific and philosophical triumph, a testament to human curiosity, persistence, and ingenuity. Today, the Oort Cloud continues to inspire astronomers and space enthusiasts alike. Each newly discovered long-period comet is a reminder of Oort's insight, a tiny emissary from a hidden frontier at the edge of the solar system. Modern technology may one day allow us to image individual objects in the cloud directly, but for now we rely on their journeys, their orbits, and the careful predictions of celestial mechanics. Every comet confirms the existence of this distant, mysterious realm, reinforcing one of the most fascinating and enduring ideas in astronomy. Jan Oort's work also highlights the importance of long-term observation. The patterns he discovered could only be seen because astronomers had been recording cometary paths for generations. It was the accumulation of data over centuries that allowed Oort to notice the subtle signals, to see the underlying structure, and to reveal a hidden region of the solar system that had always been there but invisible to the naked eye. The Oort Cloud reminds us that the universe is far more intricate and layered than first appearances suggest. While the planets and moons of the inner solar system form a relatively orderly flat plane, the distant outskirts are chaotic and mysterious, full of objects orbiting in every conceivable direction. It is a place of frozen relics, silent witnesses to the early history of the solar system, waiting patiently in the cold darkness for the rare chance to journey inward. The story of the Oort Cloud is, in many ways, the story of human ingenuity and imagination. It shows how careful observation, rigorous analysis, and creative thinking can reveal entire worlds that cannot be seen directly. It reminds us that the universe is not limited to what we can touch or photograph, but also includes realms that are inferred, hypothesized, and ultimately confirmed through patterns and mathematics. Even now, more than 70 years after Oort first proposed it, the cloud remains largely mysterious. Its sheer scale, its invisibility, and the difficulty of observing its individual components make it one of the most elusive and fascinating regions of the solar system. Yet, through the study of comets, we continue to glimpse its structure and properties, confirming Oort's predictions and enriching our understanding of the solar system's farthest reaches. Oort's legacy is a powerful reminder that the universe often reveals its secrets not through obvious signs, but through careful interpretation of subtle hints. By tracing the orbits of comets, by studying their paths across the sky, he uncovered a hidden cosmic realm. The Oort Cloud is a testament to human curiosity and intellect, a frozen, distant world that continues to inspire awe, wonder, and scientific inquiry. In essence, Jan Oort opened our eyes to the fact that the solar system is much larger and more complex than anyone had imagined. He transformed the concept of outer space from a simple emptiness beyond Pluto into a rich, dynamic and multi-layered structure. The Oort Cloud is a realm where ancient ice drifts silently in the darkness, far beyond the reach of sunlight, quietly shaping the occasional cometary visitor that lights up our skies. By recognizing the existence of the Oort Cloud, Oort fundamentally redefined the boundaries of the solar system. The planets are just one part of a vast interconnected system that stretches across unimaginable distances. Beyond the planets lies a hidden, frozen sphere, holding clues about the formation of the solar system and the early history of our cosmic neighbourhood. And though we cannot see it directly, its influence is unmistakable, traced by the comets that journey from its icy depths into the warmth of the inner solar system. Ultimately, the story of the Oort Cloud is a story of exploration and insight, of seeing the invisible and imagining the unimaginable. It is a reminder that the universe is full of hidden wonders, waiting to be discovered by those who are patient, observant, and daring enough to think beyond the obvious. Jan Oort may never have seen a single object in the cloud himself, yet through his genius, he revealed an entire hidden world, a testament to the power of human intellect and the boundless curiosity that drives us to understand the cosmos. For generations, the outer reaches of our solar system have sparked wonder, imagination, and deep scientific curiosity. Long before we even imagined distant planets like Pluto, humans speculated that the Sun might not stand alone in its quiet corner of space. Beyond the familiar planets, beyond the icy worlds that circle silently in the Kuiper Belt, there could exist a vast, hidden wilderness of frozen objects, a shadowy frontier that most eyes have never glimpsed. For many decades, astronomers and enthusiasts alike pictured this region as a single, enormous, distant cloud, a great spherical shell of icy debris encasing the solar system in all directions. This vision of the cosmos was simple, yet profoundly mysterious, a quiet halo marking the final frontier of the Sun's influence. Yet, as with many scientific ideas, simplicity eventually gave way to complexity. Observations, calculations, and a slowly growing body of data began to hint that the distant comet cloud was not merely a single, uniform layer of ice and rock. Instead, it might possess a hidden, more intricate structure, a layered system, with an outer realm that we know only through its occasional visitors, and a quieter inner domain, almost invisible, lying closer to home yet still far beyond the orbit of Neptune. This inner realm, known today as the Hills Cloud, presents one of the most fascinating and least understood mysteries of our solar system. When Dutch astronomer Jan Oort first introduced the concept of a distant cloud of comets in the year 1950, he imagined a simple scenario. Oort, a meticulous and imaginative mind, pictured a single spherical swarm of icy bodies floating silently in the depths of space, orbiting the Sun at distances so vast that they were almost beyond comprehension. These objects, though invisible to the most powerful telescopes, were inferred from the behaviour of comets that suddenly appeared from the darkness, plunging inward toward the Sun on long looping paths. Oort's insight was revolutionary. He gave a name and a structure to a region that, until then, had been only a theoretical idea. But in his initial vision, there was no concept of separate layers or hidden zones. Just one immense, distant shell encasing the solar system. As the decades passed and astronomers gathered more data on cometary motions, a more nuanced picture began to emerge. Some comets did not seem to originate from the farthest reaches of the solar system. Their orbits suggested they were coming from a region closer to the Sun, somewhere between the outer planets and the extreme boundary of the Sun's gravitational influence. It became increasingly clear that the original single-shell idea, though elegant, could not explain everything astronomers observed. Patterns in the paths of these icy wanderers hinted at a more layered and dynamic system. The outermost layer, which most people immediately picture when they hear Oort Cloud, is a vast and ethereal region stretching from roughly 20,000 to 50,000 astronomical units away from the Sun. An astronomical unit, of course, is the distance from the Earth to the Sun, about 93 million miles or 150 million kilometers. In these staggering distances, the Sun's gravitational pull is unimaginably weak. Objects in this outer region are so loosely bound that even the slightest disturbance, a passing star, a drifting molecular cloud, or the gentle tidal forces exerted by the Milky Way galaxy itself, can push them off course. It is these perturbations that occasionally send some of these icy bodies hurtling inward, creating the spectacular long-period comets that visit the inner solar system once every few thousand or even millions of years. Yet, beyond this distant, almost ethereal shell, astronomers hypothesize the existence of another hidden layer, the inner Oort Cloud, or Hills Cloud, named after astronomer Jack G. Hills, who proposed its existence in the 1980s. Hills recognized a problem. If the outer Oort Cloud were the only reservoir of comets, it would slowly be depleted over time. Long-period comets, by their nature, are not frequent visitors. They drift for millennia in the darkness of space, and the occasional cometary visitor to our inner solar system represents just a small fraction of the cloud's total population. Hill suggested that a second, more stable collection of icy bodies must exist, a cosmic storage tank quietly replenishing the outer shell as it loses material. This inner Hills Cloud is believed to extend from around 2,000 or 3,000 astronomical units from the Sun out to approximately 20,000 or 30,000 astronomical units. To put that in perspective, Neptune, the most distant known planet, orbits at about 30 astronomical units. Thus, the Hills Cloud lies far beyond the planets we are familiar with, yet it is significantly closer than the farthest reaches of the outer Oort Cloud. The icy objects in this inner domain are held tightly by the Sun's gravity. Unlike their more distant cousins, they are rarely disturbed, remaining frozen and silent in the cosmic cold for eons, waiting patiently for the rare event that might nudge them inward. Such events might include a precise alignment of planets, the passage of a distant star, or even a subtle gravitational ripple from a nearby cloud of gas and dust drifting through the galaxy. If this inner cloud did not exist, the outer Oort Cloud alone could not sustain the population of long-period comets that continue to surprise astronomers today. Comets are observed with remarkable regularity, considering their extreme rarity and the immense distances they travel. This ongoing replenishment strongly suggests a hidden supply of icy objects lying closer in, yet still far from any telescope's reach, the Hills Cloud. Some scientists even estimate that the Hills Cloud may contain up to 90% of the total mass of the Oort system, meaning that the majority of the solar system's frozen bodies might be quietly waiting in this hidden inner domain rather than scattered across the outermost fringes of space. Why do we rarely observe comets originating from the Hills Cloud? The answer lies in disturbance, or the lack thereof. The inner cloud is a quiet, stable environment, unlike the turbulent outer shell where objects are more easily nudged by passing stars or galactic tides. Only occasionally does an icy body receive the right combination of gravitational pushes to dislodge it from its long, patient orbit. Once disturbed, however, the comet may first pass through the outer Oort Cloud, picking up speed as it is propelled inward, and eventually it may appear spectacularly in the night sky, its tail glowing as it nears the Sun. For astronomers, each such visitor provides a rare glimpse into the outer solar system, offering clues about the otherwise invisible Hills Cloud. The shape of the Hills Cloud may also differ from the outer Oort Cloud. The outer cloud is often imagined as a nearly perfect sphere surrounding the Sun in every direction, but the inner cloud may be more flattened, resembling a thick disk, a bloated bubble, or even an irregular structure slightly tilted relative to the plane of the solar system. These variations in shape remain speculative, based on computer simulations and the observed behaviours of comets, but they suggest a more complex architecture in the distant solar system than early astronomers imagined. Direct observation of the Hills Cloud remains impossible with current technology, leaving scientists to rely on models, simulations, and indirect evidence. To understand how this hidden cloud might have formed, we must travel back billions of years to the early days of the solar system, At that time, the giant planets, Jupiter, Saturn, Uranus and Neptune, were still forming and migrating within a vast, swirling disk of gas, dust and ice. Their immense gravitational influence scattered countless icy objects outward. Some of these bodies were flung entirely out of the solar system, lost forever to interstellar space. Others were captured in enormous elongated orbits that eventually became the outer Oort Cloud. Yet many objects fell into an intermediate zone, too far to remain with the planets, yet too close to escape entirely. These intermediate bodies are believed to have formed the inner Hills Cloud, a reserve of primordial ice and rock frozen in time. The significance of the Hills Cloud extends beyond mere numbers. It may contain some of the oldest, most pristine material in the solar system, unaltered since the solar nebula, the vast cloud of gas and dust from which the sun and planets were born, first coalesced. These icy relics could hold chemical clues about the conditions that existed over 4 billion years ago, at the very dawn of our solar system. If scientists ever devise a way to reach them, these objects might provide an unprecedented window into the origins of the sun, the planets, and perhaps even life itself. Speculation does not end there. Some researchers have suggested that the Hills Cloud may harbour larger, yet unseen bodies, dwarf planets, or perhaps even planets, silently drifting through the darkness. Unlike the planets we know, these hypothetical objects would remain invisible to our telescopes, wandering in the quiet shadows far beyond Neptune. The Hills Cloud, therefore, is not merely a reservoir of ice. It is potentially a frontier of undiscovered worlds and ancient cosmic history. Imagine standing on one of these distant objects, if one could survive the unimaginable cold and radiation. The sun would appear no brighter than a distant star, a pale point of light illuminating a frozen landscape of icy rocks and dust. Around you, other bodies would drift silently, some small, some enormous, all locked in gravitational dance with the sun, yet isolated from the warmth and chaos of the inner solar system. This is a realm of patience and stillness, where time stretches endlessly, and the smallest nudge can trigger a journey spanning thousands of astronomical units, eventually sending an icy traveller inward to blaze across the sky as a comet. The Oort Cloud, with its layered complexity, the outer shell and the inner Hills Cloud, remains one of the most haunting and mysterious frontiers of the solar system. It embodies the extremes of distance, gravity, and time. While the planets orbit in predictable paths, and the Kuiper belt lies just beyond Neptune, the Oort system extends into a realm where the sun's influence is barely more than a whisper, and even the tiniest gravitational ripple can set massive icy objects on journeys of unimaginable scale. For scientists, every comet that appears from the darkness is a messenger from this hidden region. Long-period comets, with their slow, sweeping arcs, reveal the structure and population of the outer cloud. Occasionally, the inner Hills Cloud contributes its own traveller, a silent witness to the solar system's earliest moments. By studying their orbits, compositions and behaviour, astronomers piece together the story of a dynamic and layered outer solar system, one that has preserved the fossilised remnants of billions of years of cosmic evolution. The Hills Cloud also offers answers to long-standing puzzles. Without an inner reservoir, the continuous appearance of new long-period comets would be inexplicable. The outer Oort Cloud alone would have been gradually emptied over eons, yet comets continue to arrive. The Hills Cloud, quietly refilling the outer shell, explains this replenishment, suggesting a vast hidden network of icy objects silently maintaining the balance of the solar system. Despite decades of study, the Hills Cloud remains almost entirely theoretical, inferred only through careful observation, mathematical modelling, and computer simulations. Unlike planets or moons, it cannot be seen directly, yet its existence is strongly supported by indirect evidence. The patterns of cometary orbits, the need for a stable source to replenish the outer Oort Cloud, and the understanding of how the early solar system scattered material outward. All these clues point to a layered, intricate system far more complex than the simple spherical shell first imagined by Jan Oort in 1950. In a sense, the Oort system, the outer Oort Cloud and the Hills Cloud together, is the ultimate cemetery and archive of the solar system's forgotten and ancient objects. Each icy body is a time capsule, preserving the composition, temperature and history of the early solar nebula. Studying them, even from afar, allows scientists to reconstruct the formation and evolution of our planetary neighbourhood. It may even provide insights into planetary formation in other star systems, where similar clouds of icy debris could exist, waiting to be discovered. Every observation, every orbital calculation adds a small piece to the puzzle, gradually revealing the architecture of a realm so remote and silent that it feels almost like a dream. In conclusion, the Oort Cloud is far more than just a single, distant halo of ice. It is a layered, dynamic, and haunting frontier, encompassing the outer shell that occasionally sends comets plunging toward the Sun and the inner Hills Cloud, quietly storing the vast majority of the solar system's ancient icy bodies. The Hills Cloud, lying between 2,000 or 3,000 and 20,000 or 30,000 astronomical units from the Sun, act as a cosmic reservoir, maintaining the outer cloud's population and preserving the chemical fingerprints of the early solar system. It may even hide larger unseen worlds drifting silently in the darkness. Together, these two hidden layers represent one of the most mysterious and least understood regions of our cosmic neighbourhood, a place where time moves differently, where silence reigns, and where the frozen remnants of billions of years wait for the rare chance to journey inward and briefly illuminate our skies. Far beyond Neptune, in the quiet cold of space where the Sun is just another distant star, the Oort system patiently keeps its secrets. Could it be the final resting place of the solar system's forgotten pieces? Could it hold clues to the formation of planets, the origin of comets, and the very birth of our Sun? We do not yet know, but one thing is certain. The Oort Cloud, with its twin layers, the outer shell and the Hills Cloud, is a testament to the vast, mysterious and beautiful complexity of the cosmos, a frontier of silence, ice, and time that continues to challenge our understanding and inspire our imagination. The story of the Oort Cloud, and indeed of our entire solar system, begins not yesterday or a mere million years ago, but an astonishingly long time ago, more than 4,500,000,000 years in the past. Picture a universe still young and full of restless energy, a cosmos where stars and planets were being born and destroyed in a continual dance of creation and chaos. At the centre of what would become our solar system, a newborn star, the one we call the Sun, had just awakened, bursting into brilliance from the swirling remnants of a giant cloud of gas and dust. This cloud, called a nebula, was enormous, hundreds of times larger than the space we now occupy, and within it lay the seeds of worlds yet to be formed. As the Sun ignited and began to shine, it unleashed a torrent of light and heat, sending waves of energy rippling through the surrounding gas. Around this young star, countless clumps of matter, some the size of boulders, others no larger than grains of sand, spun and collided in a stormy ballet. In this chaotic maelstrom, fragments crashed together, broke apart, and recombined in an endless cycle of formation and destruction. Some of these clumps grew into mighty planets, swelling in size as they absorbed more and more material. Others were swallowed up by these growing worlds, disappearing forever into planetary cores, and many more, especially the smaller, weaker fragments, were pulled straight into the Sun, consumed by its burning heart in a blaze that erased them from existence. Yet not all matters found a home. Some fragments were neither large enough to become planets, nor close enough to be captured by the Sun. These lonely wanderers were cast outward, flung into the cold, dark reaches of space, far beyond the known planets. Over countless millions of years, these exiled pieces slowly gathered into a vast diffuse swarm, a mysterious and hidden cloud that would come to be known as the Oort Cloud. The existence of this remote region was first suspected not by seeing it directly, because no telescope has ever captured an image of it, but by observing the behaviour of comets. Comets, those sparkling visitors that streak across the night sky, carry within them ancient clues about the solar system's youth. When a comet ventures close to the Sun, the heat begins to melt its icy surface, releasing gas and dust that form the spectacular glowing tail we often see from Earth. But this tail is more than just a pretty show. It is a messenger from the distant past. The icy particles, frozen gases, and carbon-rich compounds within the comet's body have been preserved almost perfectly, having spent billions of years in the remote shadows, far from the destructive effects of sunlight and cosmic radiation. In effect, each comet is a time capsule, a tiny fragment of the universe's ancient history that arrives at our doorstep. These observations led astronomers to suspect that the Oort Cloud is not a smooth, perfect sphere, as one might imagine a planet's orbit or a crystal ball. Instead, it is far more chaotic, more like a colossal junkyard at the very edge of the solar system. Its occupants are misfits, leftovers of creation, fragments that never found their place in the grand design. Some are misshapen, fractured, or partially shattered. Others may be mixtures of rock and ice, fused together by chance collisions in the turbulent early years. There is almost no uniformity. Each object is unique, a solitary witness to the trials and chaos of a solar system in its infancy. The Oort Cloud, in this sense, is a monument to imperfection, a sprawling archive of cosmic debris frozen in time. How did so many objects find themselves in this desolate outer region? The answer lies partly with the giant planets, Jupiter, Saturn, Uranus, and Neptune. Especially the first two, the enormous gas giants. As these planets grew, their immense gravitational fields acted like celestial slingshots. Smaller bodies wandering near them could be catapulted outward at incredible speeds, sent careening into distant orbits that might take millions of years to settle. Many of these objects never completely escaped the sun's pull. They were captured into enormous looping trajectories that eventually stabilized into the diffuse spherical halo we now imagine as the Oort Cloud. It is a testament to the sheer scale and power of the giant planets that they could shape a region so far from their immediate influence, sculpting a graveyard of wandering fragments into a loosely bound, far-flung collection of icy bodies. Yet the planets were only part of the story. The galaxy itself, the vast Milky Way in which our solar system drifts, has also left its fingerprints on this distant frontier. As the Sun orbits the centre of the galaxy, it occasionally passes near other stars, through clouds of gas, and even near the remnants of other solar systems. Each encounter, though minor in effect, sends tiny gravitational nudges outward, subtly shifting the orbits of objects on the fringes. Over millions and billions of years, these minor disturbances accumulate, gradually spreading the Oort Cloud's residence farther apart, stretching its limits and shaping its uneven structure. It is as if the galaxy itself participates in the creation of this distant wilderness, whispering imperceptible adjustments to the orbits of icy bodies over timescales that dwarf human understanding. Interestingly, some of the objects in the Oort Cloud may not even be originally from our Sun. Astronomers speculate that, in its earliest days, the Sun was born in a dense stellar nursery, a crowded region filled with hundreds or even thousands of other young stars. In such a bustling environment, gravity is a mischievous force, capable of stealing fragments from one star to pass them to another. It is conceivable, therefore, that some icy wanderers in the Oort Cloud began life around neighbouring stars, only to be captured by the Sun's gravity during a close stellar encounter. If this is true, then the Oort Cloud is not merely a storage area for the solar system's discarded remnants. It may also be a collection of fragments from multiple suns, a cosmic patchwork of distant origins brought together in one frozen, silent wilderness. The sheer scale of the Oort Cloud is almost beyond comprehension. Estimates suggest that it holds far more material than all the comets we have ever observed, combined many times over. The comets we occasionally see blazing across the sky are only the rare few that have been dislodged from the distant reaches and sent on a trajectory inward toward the Sun. For every one of these dazzling visitors, there may be thousands more lying quietly in darkness, untouched, unobserved, and undisturbed. This also explains the sudden appearance of strange comets on unusual paths, comets that seem to materialize from nowhere, defying the patterns we have come to understand. These are the hidden residents of the Oort Cloud, finally venturing inward after billions of years in cold exile. Within this remote icy frontier, silence dominates. There is no warmth, no light except for the faint distant glow of the sun, as it appears like a tiny pinprick in the sky. There is no sound, for sound requires air or another medium to travel through, and the vacuum of space provides none. The distances between objects are immense, vast beyond human comprehension. Collisions, already rare, occur with even less frequency in this frigid emptiness. Motion is agonizingly slow. An object may take millions of years to complete a single orbit around the Sun. Time itself seems to stretch differently in this lonely realm, a slow and silent guardian of the past. It is, in every sense, the loneliest and most isolated region of our solar system, a place so distant that our familiar planetary neighbourhood seems like a bustling metropolis by comparison. Scientists often describe the Oort Cloud as a cosmic archive, a frozen library containing the raw ingredients of our solar system's formation. Every icy fragment, every frozen particle, is a record of conditions that existed more than 4 billion years ago. In these fragments, the story of the solar system's birth and its earlier struggles is preserved, almost untouched by the chaos of later cosmic events. But there is another, darker way to envision this remote expanse. Some describe it as a cemetery in space, not a place of traditional burial, but a graveyard of abandonment. Here lie broken worlds, forgotten fragments, and shattered remnants, each one adrift, never able to find a home, floating endlessly in solitude. The Oort Cloud challenges our ideas about where the solar system ends and where interstellar space begins. If we imagine the planets, the asteroid belt, the Kuiper belt, and even the distant icy worlds of Pluto and beyond as part of the solar system, then the Oort Cloud represents its extreme frontier, the outermost limit before the vast emptiness between stars begins. Beyond it lies the true interstellar medium, the vast expanse that stretches between the stars, filled with diffuse gas, cosmic rays, and the faint glow of distant suns. The boundary between the Oort Cloud and interstellar space is not sharply defined, but it represents the threshold between the familiar neighbourhood of the Sun and the infinite uncharted cosmos beyond. To understand the Oort Cloud is also to glimpse the sheer patience of the universe. Its objects have been drifting in frozen isolation for more than 4 billion years. They are remnants of a time before life existed on Earth, before continents drifted to their current positions, and before the dinosaurs even walked the planet. These distant icy bodies have experienced none of the warmth, none of the turbulence that shaped the inner planets. They are untouched archives of a time long gone, witnesses to the Sun's earliest eruptions, the collisions that formed planets, and the slow gravitational tugs of their distant neighbours. The Oort Cloud is more than just a distant collection of debris. It is a mirror reflecting the history of the entire solar system. Its icy inhabitants tell the story of creation, survival, and exile. Some of the fragments may one day journey inward, swept along by gravitational disturbances from passing stars or wandering interstellar clouds, becoming the comets that surprise and awe us in the night sky. Others will remain in quiet solitude, drifting eternally in the cold darkness, their histories unrecorded, their stories unshared, until the end of time itself. Astronomers continue to study these distant realms indirectly, learning about them through the behaviour of comets, the subtle gravitational effects on other bodies, and the rare occasional glimpses of objects that stray inward. Every discovery provides a new clue about the Oort Cloud's formation, its structure, and its role in the broader cosmic story. It is a frontier that pushes the limits of imagination, a place so far removed from human experience that it seems almost mythical, yet it is as real as the Sun and planets we see every day. The mystery of the Oort Cloud also invites profound philosophical questions. What does it mean for a fragment to drift for billions of years without ever finding a home? How do we define the edge of our solar system when such an immense, diffuse region exists? And what can these icy remnants teach us about the origins of life, the processes of planetary formation, and the nature of cosmic time itself? Each question points to the fact that the Oort Cloud is not just a physical space, it is an idea, a concept that stretches human understanding, bridging the gap between what we can see and what lies far beyond the reach of our eyes. In conclusion, the Oort Cloud is a frozen, distant and enigmatic realm, more vast than the imagination can easily grasp. It is a chaotic collection of fragments flung from the inner regions by the immense gravity of giant planets, shaped further by the slow nudges of the Milky Way, and possibly supplemented by fragments captured from other stars. It's a realm where time moves slowly, where silence reigns supreme, and where every fragment carries the history of our solar system within it. Some call it a cosmic archive, others a graveyard of forgotten worlds, but all agree that it represents the ultimate frontier of our Sun's domain. Beyond the planets, beyond the Kuiper belt, Beyond the icy worlds we have begun to explore, the Oort Cloud stretches outward into the darkness, a final frozen threshold before the infinite expanse of interstellar space begins, a place of mystery, solitude, and awe-inspiring scale. To look at the Oort Cloud in one's mind is to peer into the distant past, to imagine the chaotic birth of our sun, to feel the quiet power of gravity shaping matter over billions of years, and to recognize that even in the loneliest corners of our solar system, the story of creation continues to whisper, frozen in ice, waiting patiently for someone to listen. It is, quite possibly, the most remote and secretive region we have ever imagined, a distant halo of ice and rock at the very edge of the sun's influence, marking the boundary between the known and the unknown, the familiar and the infinite, the home of our solar system and the vast cosmos beyond. For centuries, humans looked up at the night sky and imagined that the solar system, the collection of planets, moons, asteroids and comets that orbit the sun, was neatly contained, like a room with invisible walls. Beyond the last known planets, it seemed, there was nothing. The sun's family ended with Neptune, or perhaps with Pluto, if one counted the small distant worlds that inhabit the frozen outskirts of our system. The idea that our solar system might extend far beyond these familiar planets was unimaginable to those early observers. For them, space beyond the planets was an endless void, empty and silent, where the sun's influence could no longer be felt. Yet, as our knowledge of the cosmos grew, a more subtle truth began to emerge. The sun's reach is far greater than the paths traced by the planets. Its gravitational pull, its light, its steady wind of charged particles, all these extend across a region so vast that the human mind struggles to comprehend it. The solar system is not simply the area where the planets circle. It is an enormous layered expanse that blends gradually into the wider galaxy. Determining exactly where it ends is far from straightforward, and it depends entirely on how one chooses to define its edge. One of the simplest ways to think about the boundary of the solar system is through gravity. Every object, no matter how small or distant, is affected by the sun's pull. This includes the faintest icy comet drifting silently in the far reaches of space. By this measure, the solar system stretches astonishingly far. Some calculations suggest that the sun's gravitational influence could reach nearly 2 light-years outward. To put that into perspective, 1 light-year is the distance light travels in a single Earth year, about 6 trillion miles. 2 light-years is nearly 40 trillion miles, or roughly halfway to our nearest stellar neighbour, Proxima Centauri. It is a scale so vast that it is almost impossible for the human imagination to grasp. If the solar system were a city, Neptune would be a house on the edge of town, while the outer boundary of gravity would be a distant forest on the horizon, stretching far beyond any visible landmark. Gravity, however, is not the only way to define the solar system's limits. There is another boundary, shaped not by invisible pull, but by the flow of matter and energy. Surrounding the sun is a protective bubble called the heliosphere. This enormous invisible bubble is created by the solar wind, a constant stream of charged particles that flows outward from the sun in all directions, moving like an invisible tide through the emptiness of space. The solar wind pushes against the thin gas and dust that drift between stars, forming a shield that keeps the inner regions of our system relatively protected from the harsh galactic environment. The edge of this bubble is called the heliopause. Beyond this point, the solar wind can no longer fight against the pressure of the interstellar medium, the mixture of gas, dust, cosmic rays, and magnetic fields that fills the space between stars. The heliopause is a dynamic, shifting frontier. Its distance from the sun changes depending on solar activity, which waxes and wanes in cycles roughly 11 Earth years long, and on the local density of interstellar material. On average, scientists believe the heliopause lies about 120 times the distance from the Earth to the Sun. To visualize this, imagine a line stretching from the Sun to the Earth, repeated 120 times in a straight path. Even at this enormous distance, the heliopause still lies deep within the outer reaches of the Oort Cloud, a distant shell of icy objects that mark the true far edges of the Sun's gravitational domain. A milestone in human exploration of this hidden frontier came in the year 2012. Voyager 1, a small but remarkably durable spacecraft launched back in 1977, crossed the heliopause and entered interstellar space. For the first time in history, a human-made object had left the Sun's solar wind bubble behind. Beyond the heliopause, Voyager 1 encountered a new cosmic environment, where particles and magnetic fields no longer came from the Sun, but from the galaxy itself. Scientists celebrated this achievement, recognizing it as the first step toward understanding the distant realms of space that had long existed only in theory. Yet even Voyager 1 had not truly escaped the solar system, at least not if we define the boundary by gravity. The Sun's pull still dominates its trajectory, and the spacecraft will likely remain under solar influence for many years, perhaps even centuries, before it drifts beyond the outermost reaches of the Oort Cloud. The heliopause may signal the transition from the Sun's immediate environment to interstellar space, but the Sun's gravitational tug extends much further, like an invisible string holding the outermost comets and icy bodies in orbit. This brings us to the remarkable Oort Cloud, a vast spherical shell of icy objects that drifts silently at the edge of our solar system. Named after the Dutch astronomer Jan Oort, who first proposed its existence in the mid-20th century, this cloud is unlike anything most people have ever imagined. It is far too distant and faint to be seen with telescopes, yet it exists as a kind of ghostly boundary, a region where the Sun's influence still holds sway, even as it fades against the immense backdrop of the galaxy. The Oort Cloud is not solid, nor is it neatly ordered. It is a vast collection of icy bodies, ranging in size from small rocks to objects dozens of kilometers across, loosely bound to the Sun by gravity. In this in-between zone, the solar system begins to blur into interstellar space. Life in the Oort Cloud is tranquil, but not completely still. Objects in the outer edges are held only weakly by the Sun's gravity, meaning that distant stars passing nearby can exert a gentle tug, nudging some of these icy bodies into new trajectories. Over millions of years, these small perturbations accumulate. Occasionally, a comet is knocked inward toward the inner solar system, becoming the long-period comets that, once in a while, streak across our skies with glowing tails visible to the naked eye. Other bodies are pushed entirely free, drifting off into the galaxy to become wandering nomads, lost to our Sun forever. Stars do not remain static in the galaxy, and neither does the Sun. Our solar system drifts along a vast orbit around the centre of the Milky Way galaxy, taking hundreds of millions of years to complete a single revolution. Along this journey, we pass through regions of space with varying densities of stars, gas, and dust. Sometimes a neighbouring star drifts close to the solar system. Of course, close in this context is a relative term. Even a star passing within a single light year, a distance roughly 63,000 times the span from the Earth to the Sun, is considered nearby. At such distances, the star's gravity can still tug gently at the outer Oort Cloud, subtly reshaping the solar system's distant boundaries. These gravitational interactions are slow on human timescales, almost imperceptible within a single lifetime. But over millions or even billions of years, they leave a mark. They reshape the Oort Cloud, push comets into new orbits, and sometimes send icy bodies hurtling inward, creating spectacular celestial shows for those of us who look up at night. In this way, the solar system is not a fixed, unchanging entity. It is a dynamic system, moulded by internal forces and external encounters alike. In addition to gravity, the Sun's influence extends through its light and radiation. Even in the deepest reaches of space, sunlight travels outward, weakening gradually until it is overtaken by the light of other stars. This creates yet another way to imagine the solar system's boundary, the point where the Sun is no longer the brightest beacon in the sky. Like the heliopause or the Oort Cloud, this edge is not sharply defined. It fades slowly, blending the Sun's influence into the diffuse light of countless stars. It is a gentle transition, not a wall or a curtain. The very concept of interstellar space is flexible too. Scientists generally use it to describe the regions between stars, not just the space beyond the planets. But even interstellar space is far from empty. It is filled with gas, dust, radiation, and magnetic fields. It is an active, dynamic environment shaped by the motions of stars, supernova explosions, and the swirling currents of the galaxy itself. As our solar system moves through this medium, it pushes outward, creating a bow wave-like effect similar to the ripples that form at the front of a boat moving through water. This interaction shapes the heliosphere and helps define the transition from the Sun's local bubble to the wider galaxy. The boundary between our solar system and interstellar space is therefore not a line but a layered region, like a fog that becomes denser as one moves away from a light source. The inner regions of the solar system are dominated by the planets, moons, and the inner belt of asteroids. Farther out lies the Kuiper Belt, a band of icy worlds beyond Neptune, including Pluto and other dwarf planets. Beyond this lies the scattered disk with objects in elongated, sometimes erratic orbits. And finally, the Oort Cloud marks the outermost boundary, a tenuous, ghostly shell slowly blending into the galaxy itself. Within this complex system, human-made probes like Voyager 1 offer a rare window into the unknown. These spacecraft move slowly, taking decades to reach the outer reaches of the solar system, and their signals take years to return to Earth. Yet every measurement brings new insight. Through them, we begin to understand how the Sun's gravity, its light, and its wind of particles interact with the interstellar medium. We learn how the heliosphere changes with solar cycles, and how distant stars influence the Oort Cloud. Each piece of data adds to a picture of a solar system that is alive, moving, and interwoven with the galaxy. The Oort Cloud, in particular, is a remarkable bridge. It is the outer skin of our solar system, a region where the Sun's influence still matters, but is no longer dominant. Beyond it, other stars take over, and the gravitational landscape is shared with countless other suns. There is no sudden crossing, no line in the sand. Instead, the transition is gradual, a soft fading into interstellar space. Objects in this region are shaped by a slow tug-of-war between the Sun and the rest of the galaxy. Some may already be wandering away, unmoored by the gravity of passing stars or by subtle perturbations over millions of years. Others remain loosely bound, drifting along invisible pathways dictated by forces both near and far. As the solar system travels through the Milky Way, it encounters regions of space with different densities of stars, gas, and cosmic dust. Sometimes, it passes through crowded neighborhoods, full of stars and stellar debris. At other times, it moves through quieter regions. Even a single nearby star can exert influence over the Oort Cloud, nudging comets onto new paths. These interactions, repeated over millions of years, slowly reshape the outer boundary of the Sun's domain. Ultimately, the solar system is not a static, neatly defined place. It is a fluid, dynamic structure, stretching from the innermost planets to the outer edges of the Oort Cloud, and beyond that, blending seamlessly into the galaxy. Its boundaries depend on how we measure them, by planetary orbits, by the reach of the solar wind, by the power of gravity, or by the Sun's fading light. Each method offers a different story, and together they reveal a system far larger, more complex and more wondrous than most of us can imagine. From the perspective of human history, our understanding of these distant regions is only just beginning. For centuries, the planets were thought to mark the outer limit. For decades, the heliosphere has provided a measurable, though shifting, boundary. Today, spacecraft like Voyager 1 offer direct contact with interstellar space, while telescopes and simulations reveal the structure of the Oort Cloud. Tomorrow we may venture further, sending probes even deeper into this unseen frontier. Each new journey teaches us more about our place in the galaxy, the subtle interactions that shape the solar system, and the vastness that lies beyond our familiar planetary neighborhood. The solar system is, in every sense, a grand, moving ocean. The Sun is the anchor, its gravity and light shaping everything in its vicinity. Planets, moons, asteroids and comets drift in this gravitational sea, while the outermost icy bodies of the Oort Cloud form a boundary that is both fragile and enduring. Beyond this, the galaxy stretches endlessly, filled with stars, nebula, and cosmic mysteries. The transition from the solar system to the galaxy is not a wall but a misty threshold, a place where the familiar fades and the unknown begins. In this grand cosmic dance, nothing exists in isolation. The Sun moves through the Milky Way, carrying its planets, moons, and distant comets along for the ride. The Oort Cloud responds to passing stars, the solar wind pushes outward into interstellar space, and the faint light of the Sun gradually gives way to the glow of distant suns. Even at the farthest reaches, we can trace the Sun's influence, faint but unmistakable. For many decades, astronomers have been quietly piecing together an astonishing cosmic puzzle. They have studied the slow, steady paths of comets, those icy wanderers that occasionally sweep through the inner reaches of the solar system, and tried to trace their origins back to distant corners of space. These icy travellers are not random. They follow precise, elongated orbits, and over time, scientists realised that their paths might carry subtle hints about the movements of stars far beyond the planets. The idea is simple in concept, but immensely complex in execution. By comparing the known trajectories of comets with the historical positions of stars that might have passed near our Sun, researchers can sometimes identify a connection, like finding fingerprints at the scene of a crime that happened tens of thousands of years ago. Among the few stellar suspects that have emerged in this cosmic investigation, one name stands out: Schultz's star. This is not a bright, flashy star visible in the night sky, but a faint, dim red dwarf, barely noticeable even with modern telescopes. Yet, it holds a story that stretches deep into our solar system's past. Roughly 70,000 years ago, an eye blink in cosmic time, Schultz's star is believed to have drifted unusually close to our Sun. Close, in this context, means perhaps less than a single light-year away, threading its way through the outermost layers of a vast mysterious region known as the Oort Cloud. Imagine for a moment a tiny celestial interloper passing through the outskirts of a massive sphere of icy debris, nudging countless frozen bodies ever so slightly. That small disturbance would have been enough to alter their delicate orbits, sending some of these icy objects on a slow, millennia-long journey inward toward the Sun. Many of these icy travellers may still be wandering through the cold darkness of space, only now approaching the inner solar system as comets that will one day grace the night sky with their glowing tails. It is easy to imagine this as a rare event, something exceptional in the quiet calm of the Milky Way. Yet, on a galactic scale, such encounters are far from unusual. Every few 100,000 years, a wandering star, or even a rogue planet without a sun of its own, drifts close enough to the Oort Cloud to disturb it. These encounters come in many shapes and sizes. Sometimes, the visitor is a massive star with gravity so strong that it can stretch and bend large swathes of icy material. Other times, it is a smaller, dim red dwarf, faint and almost invisible, but still capable of exerting a gentle yet meaningful gravitational tug. Over billions of years, these countless, seemingly random interactions leave their mark on the Oort Cloud. Some regions are stretched thin, others thickened or distorted. The result is not a perfect, smooth shell, but a wobbling, uneven sphere shaped by an invisible multitude of cosmic hands. Yet the stars are not the only force shaping this mysterious cloud. The Oort Cloud exists within a larger gravitational environment, subject to the persistent pull of the Milky Way galaxy itself. Just as the Moon tugs at Earth's oceans to create tides, the combined gravity of billions of stars, clouds of gas, and the invisible pull of dark matter exerts a subtle but constant influence on the distant edges of our solar system. This galactic tide, as scientists call it, stretches the Oort Cloud in certain directions, loosens objects at its periphery, and gradually works to pry material away from the Sun's embrace. Over billions of years, the combined effects of passing stars and the steady hand of the galaxy have sculpted the Oort Cloud into its present form, roughly spherical, a distant halo of frozen objects that encircle our Sun like a protective yet fragile shell. In fact, it is precisely these repeated disturbances that may be essential to the Oort Cloud's very existence. Without them, many of the icy objects would remain locked in place, frozen in silent orbit for eternity, undisturbed and unseen. But occasional nudges, whether from a passing star or the gentle tug of the galactic tide, create imbalances that set some objects drifting toward the inner solar system. Over millions of years, these wandering bodies become the comets we sometimes see streaking across our skies, leaving glowing tails in their wake. In a sense, the comets are messengers, carrying with them the story of ancient gravitational interactions that began long before humanity existed. However, the same forces that send comets inward can also strip away parts of the Oort Cloud entirely. Over the 4.5 billion years of the solar system's life, it is likely that the Oort Cloud has already lost a significant portion of its original icy population. Some objects, once tightly bound to the Sun's gravity, have been ejected into interstellar space, now roaming freely in the vast darkness between stars. These untethered objects drift endlessly, hidden from view, creating a diffuse population of wandering ice in the galaxy. Other solar systems are likely in similar situations, having lost parts of their own outer clouds through comparable encounters. As a result, the outskirts of space are probably a chaotic mix of native and captured icy bodies, each telling a story of ancient celestial encounters. It is even conceivable that our own Oort Cloud contains a few icy fragments that were stolen from other stars during close cosmic brushings, captured by the sun's gravity and added to our distant frozen halo. Amid this dynamic, ever-changing history of the Oort Cloud, some ideas have taken on a particularly dramatic and intriguing flavour. One of the most captivating involves a hypothetical hidden star, a companion to the Sun, proposed in the early 1980s to explain mysterious patterns in Earth's own history. Around this time, physicists led by Richard Muller were examining the fossil record, studying the timing of mass extinction events, moments in the past when vast numbers of species suddenly disappeared from the planet. What they noticed was strange. These catastrophic events did not appear to be completely random. Instead, there seemed to be a rough cycle, with extinctions occurring approximately every 26 million years. This observation sparked bold speculation. Could these recurring mass extinctions be caused by something far beyond Earth, in the outer reaches of the solar system? Perhaps enormous icy bodies from the Oort Cloud were being nudged inward on a periodic schedule, striking the inner solar system and indirectly affecting life on our planet. But if so, what could be responsible for disturbing these distant comets so regularly? This question led to the audacious suggestion that the Sun might have a hidden companion, a distant dim star orbiting far beyond the planets, silently tugging at the outer edges of the Oort Cloud and occasionally sending comets hurtling toward the inner solar system. The theoretical star, if it existed, would only approach the Oort Cloud every 26 million years or so, creating bursts of cometary activity at intervals long compared to human lifetimes but brief in the cosmic scale. Scientists imagine this hidden partner as small, dark, and extremely difficult to detect, almost like a ghost in space. It would not shine brightly like the Sun. Perhaps it was a dim red dwarf, barely producing light, or even a brown dwarf, a type of failed star that never ignited enough nuclear fusion to shine like a true star. Finding such an object would be a monumental challenge, requiring years or even decades of careful observation. Yet, if it did exist, it could provide an elegant explanation not only for the recurring pattern of mass extinctions on Earth, but also for sudden surges of cometary visitors that appear from the depths of the Oort Cloud at seemingly predictable intervals. This hypothetical companion was given a fittingly ominous name, Nemesis. In Greek mythology, Nemesis was the goddess of vengeance, a hidden force that punished wrongdoers and restored balance. In the cosmic context, the Sun's hidden companion was envisioned as far from benevolent. Dark, distant, and capable of causing significant disruption, Nemesis would be a quiet but potent agent of change at the edges of the solar system. The concept captured the imagination of both scientists and the public, offering a thrilling possibility that the Sun is not alone in its journey through the Milky Way. Perhaps the Oort Cloud is not shaped solely by passing stars or the gentle pull of the galaxy, but is subtly tugged, ever so slightly, by a mysterious partner lurking in the shadows. For many years, astronomers conducted a determined search for Nemesis. They scanned the skies with infrared telescopes, capable of detecting cold, dim stars or brown dwarfs. They examined large portions of the celestial sphere, looking for the faintest hint of a hidden companion. Yet each search ended in disappointment. No object was found in the expected range. If Nemesis exists, it must be extraordinarily faint, incredibly distant, or both, slipping through even the most sensitive surveys like a phantom. These repeated failures led some to doubt its existence, yet the notion was never fully dismissed. After all, stars rarely travel entirely alone. Observations of our galaxy show that more than half of all Sun-like stars are part of binary or multiple star systems. Twins, trios, or even larger groups are common. From this perspective, the idea of the Sun having a companion, while extraordinary, is not impossible. Perhaps our solar system originally formed with two suns, and one was ejected early in its history, leaving only a faint distant partner behind. Or perhaps Nemesis has always orbited at an immense distance, a silent witness to the slow evolution of the solar system. The scientific intrigue does not end there. The possible presence of Nemesis fits within a broader pattern of galactic interactions that have shaped the Oort Cloud over billions of years. Just as Schultz's star may have nudged icy objects inward 70,000 years ago, and countless other stars may have influenced the cloud over time, Nemesis, if it exists, would be part of a long history of gravitational encounters that gradually sculpt the outer solar system. Each push and pull, whether from a nearby star, the galactic tide, or a hidden companion, contributes to the complex, lopsided and dynamic structure of the Oort Cloud. Far from being a simple, smooth sphere of ice, it is a living record of gravitational influences that have acted over billions of years, a cosmic diary written in frozen bodies orbiting in the coldest reaches of our Sun's influence. Beyond Nemesis, astronomers continue to investigate other fascinating possibilities. Could parts of the Oort Cloud contain icy objects captured from other star systems during ancient close encounters? Could wandering rogue planets have passed through the cloud, temporarily disturbing its balance? Could the occasional surge of comets toward the inner solar system herald the approach of a faint unseen interloper like Schultz's star in the distant past? Each of these questions opens a door to further exploration, offering glimpses into the dynamic, interconnected nature of our galaxy. Ultimately, the study of the Oort Cloud is more than a study of icy rocks at the edges of the solar system. It is a story about motion and time on the grander scale, about the interactions between stars and the invisible forces that shape entire systems. It tells us that the solar system is not isolated, but is part of a vast, living galaxy, where stars drift, gravity tugs, and time stretches unimaginably far. Comets are more than mere curiosities. They are emissaries from the past, reminders of encounters that happened tens of thousands, millions, or even billions of years ago. Every icy object carries with it a history of forces, some gentle, some violent, that have nudged it out of place and set it on a journey through the solar system. The hypothetical Nemesis adds a layer of drama to this story. Whether real or imagined, it serves as a symbol of the hidden influences that may shape cosmic events in ways we are only beginning to understand. It reminds us that the universe is not static, but is full of unseen connections, subtle nudges, and grand cycles of action and reaction. Every passing star, every tug from the galactic tide, and every potential hidden companion is part of a web of forces that has gradually shaped our solar system over billions of years. These forces have guided comets from the farthest reaches of the Sun's influence to dazzling arcs across our night sky, occasionally reminding life on Earth of the vast, interconnected cosmos we inhabit. Far beyond the familiar planets of our solar system, in a region so distant that sunlight becomes but a faint glimmer, lies a domain of quiet, frozen mystery. This is the realm of the Oort Cloud, a vast, nearly invisible shell of icy bodies that drift in tenuous orbits around the Sun. For decades, astronomers have wondered what secrets might be hidden there. Could there be massive, unseen objects, silent sentinels of the outer solar system, slowly wandering through the darkness? One of the most intriguing ideas to emerge is the possibility of a companion to our Sun, a mysterious object that traces a vast, looping orbit over tens of millions of years, far beyond the planets and even beyond the farthest comets. If such a companion exists, its journey through space would be unimaginably slow, almost glacial. Picture it moving along a path so enormous that it takes tens of millions of years to complete a single orbit around the Sun. And yet, even in this distant, shadowed realm, the gravitational influence of such an object could be profound. As it passes near the outer edge of the Oort Cloud, its gentle tug might be enough to disturb the delicate balance of countless icy bodies, sending some of them tumbling inward toward the inner solar system. Most would sail past the Earth harmlessly, invisible and silent. Others might streak across the sky in brilliant displays, dazzling observers for brief fleeting moments. But occasionally, one of these icy travellers could be large enough to strike the Earth itself, potentially triggering cataclysmic changes in the course of life. Models of these interactions suggest a kind of cosmic rhythm, a subtle sweep through the outer solar system. The hypothetical companion, sometimes referred to in speculative theories as Nemesis, would not need to come particularly close to exert its influence. The Oort Cloud is so loosely bound to the Sun that even distant nudges can destabilize it. And because this companion's orbit would be so vast and drawn out, such visits would be extremely rare, separated by tens of millions of years. Interestingly, some scientists have speculated that this rhythm could correspond, in a broad sense, to certain patterns of extinction seen in Earth's deep past. Could there be a connection between the slow passage of a hidden companion and the waves of a life's destruction and renewal? The nature of this hypothetical object is debated. It may not even be a star. Some theories suggest that it could be a massive planet, far larger than Jupiter, lurking unseen in the dark expanses beyond the known planets. In recent years, discussions of a Planet 9, a massive and still unobserved planet beyond Neptune, have captured the imagination of astronomers. Planet 9 is thought to influence the orbits of distant Kuiper belt objects, subtly guiding their paths over millions of years. While Planet 9 would lie much closer to the Sun than a Nemesis-type companion, the underlying idea is similar. There could be unseen forces at work in the far reaches of our solar system, shaping the movement of icy and rocky bodies far beyond the familiar planets. Skepticism about such hypotheses is healthy and widespread. Critics caution that patterns of extinction on Earth, if they exist at all, may have numerous explanations. Climate fluctuations, volcanic eruptions, asteroid impacts, or even sheer randomness might account for observed cycles in the fossil record. Without direct evidence of a companion star or planet, Nemesis remains firmly in the realm of speculation. Yet even as a theoretical idea, it emphasizes an important truth. The solar system's boundary is not sharply defined. The Oort Cloud, with its billions of icy objects, represents a frontier that is deeply connected to the wider galaxy, where unseen forces and wandering stars may reach across light years to leave subtle fingerprints on our planetary system. The outer solar system, beyond the orbit of Neptune and even past the Kuiper belt, remains a largely unexplored wilderness. Humanity has sent spacecraft to the inner planets, mapped numerous asteroids, and begun cataloguing the Kuiper belt's icy worlds, yet the Oort Cloud itself is ghostly and elusive. Within it, there could be a brown dwarf, a massive unseen planet, or simply millions upon millions of icy fragments, silently drifting in the deep shadows of space. It is a region of possibilities, where theories meet imagination, and where the quiet passage of an unseen companion could ripple outward to the inner planets over tens of millions of years. One particularly compelling concept connected to these ideas is the Shiva hypothesis, named after the Hindu god associated with destruction, transformation, and renewal. The hypothesis proposes that the Oort Cloud is occasionally disturbed, sending waves of comets inward toward the planets. Should one of these icy wanderers collide with Earth, it could unleash a catastrophic chain of events. Dust and debris thrown into the atmosphere could block sunlight for months or even years, causing temperatures to plummet. Crops might fail, ecosystems collapse, and food chains could unravel. In this sense, the cosmos itself becomes a sculptor of life's fortunes, wielding destruction and creation in tandem. Proponents of the Shiva hypothesis often point to one of Earth's most famous and dramatic extinctions, the disappearance of the dinosaurs. Approximately 66 million years ago, an object of enormous size struck near what is now the Yucatan Peninsula in Mexico. The Chicxulub impact crater, created by this collision, stretches over 100 miles across, a stark reminder of the force unleashed. Around the globe, a thin layer of sediment enriched with iridium, a metal rare on Earth's surface but common in comets and asteroids, marks the moment of this catastrophic impact. This layer serves as a smoking gun, strongly indicating that a space object was responsible for one of the most significant mass extinctions in Earth's history. Yet this raises an intriguing question. Why then? Could this single event be part of a recurring cosmic cycle, a periodic rhythm of cometary bombardment? The Shiva hypothesis extends this idea, suggesting that such catastrophic impacts may not be isolated incidents. Instead, they could form part of a repeating cycle, with episodes of heightened cometary activity occurring every tens of millions of years. Various mechanisms could drive such a cycle. Perhaps as our solar system slowly journeys through the Milky Way, it occasionally passes through denser regions of stars and interstellar material, creating gravitational disturbances that ripple outward to the solar system's distant outskirts. Or maybe the gravitational influence of the galaxy itself gently nudges the Oort Cloud in a repeating pattern. Regardless of the precise cause, the effect would be the same: the release of comets from their distant icy storage, sending some on slow but inexorable paths toward the inner planets. Computer models have helped scientists visualize how such disturbances might unfold. Surprisingly small changes, like a subtle tilt of the solar system or the gravitational influence of a nearby star, could be sufficient to destabilize vast numbers of Oort Cloud objects. In moments like these, thousands of icy bodies might begin their long looping journeys inward. Most would remain invisible, never making themselves known to human observers, seen only through the lenses of powerful telescopes. Yet occasionally, one could impact Earth, delivering a sudden and violent shock to the environment. Not everyone in the scientific community accepts the Shiva hypothesis without reservations. Critics argue that mass extinctions do not follow a tidy, predictable schedule. Fossil records are incomplete, fragmentary, and often difficult to date precisely. Some researchers contend that terrestrial events, giant volcanic eruptions, shifts in atmospheric composition, or changes in sea level were the primary drivers of many extinction events. Despite these debates, the notion that cosmic events might influence life on Earth persists. Increasingly, scientists are considering the possibility that cometary bombardments might arrive in clusters rather than as isolated events. In such a scenario, a single disturbance of the Oort Cloud could unleash multiple comets simultaneously, dramatically raising the odds that one might strike the Earth. A rare passage through a particularly dense region of the galaxy could unleash a wave of icy travelers racing toward the inner solar system, some of which could bear catastrophic consequences. Over the eons, Earth has endured countless cosmic impacts. Some left enormous craters etched into the landscape, while others likely struck oceans, leaving little to no visible trace. Geological processes such as erosion, plate tectonics, and sedimentation have erased much of the evidence over millions of years, yet the Moon, untouched by wind, water, and shifting plates, preserves a stark record of these collisions. Its scarred surface reminds us that massive impacts are not rare. They are recurring events in the history of our solar system. One of the most fascinating aspects of the Shiva hypothesis lies not only in its explanation of mass extinctions, but also in the patterns of life's recovery afterward. Following catastrophic events, life often rebounds in remarkable and sometimes unexpected ways. Entirely new species emerge. Ecosystems rebuild themselves with extraordinary ingenuity. Evolution, it seems, is capable of rapid bursts of creativity following destruction. In this sense, the cosmic forces that drive mass extinctions may also drive renewal. Just as the god Shiva in ancient mythology embodies destruction and rebirth, these celestial disturbances might play a similar role, perpetuating a grand cycle of death and creation on our planet. The theoretical companion star or planet, whether called Nemesis or otherwise, would represent the most distant member of our solar family. Its orbit would stretch far beyond the planets into the vast, cold darkness past comets and cosmic dust. Its returns would be rare, yet even the subtlest passage could ripple through the Oort Cloud, nudging icy bodies and setting in motion events whose consequences might not be felt for millions of years. In this way, Nemesis, though unproven, reminds us of the dynamic and interconnected nature of our cosmic neighbourhood. The edges of the solar system are not static, barren boundaries, but rather a frontier of ongoing interactions, where gravity, motion, and chance converge to shape the fates of worlds. Even as we continue to explore the solar system, the outer reaches remain a profound mystery. While we have sent probes to planets, studied countless asteroids, and begun mapping the Kuiper Belt, the Oort Cloud continues to elude direct observation. Within it could lie massive planets, brown dwarfs, or simply untold numbers of icy fragments. Any of these could act as agents of change, slowly altering the distribution of matter in the outer solar system and occasionally sending visitors inward. The vast distances involved ensure that such events are rare, yet when they occur, they can leave marks that last for millions of years. In contemplating these possibilities, we are reminded of the fragility and resilience of life on Earth. Over billions of years, our planet has faced threats from within and from the heavens. Cosmic collisions, climate shifts, and geological upheavals have tested life's endurance time and again. Yet life persists, adapts, and flourishes, often in unexpected ways. The interplay between destruction and creation, between chaos and order, is woven into the very fabric of existence. Just as the Oort Cloud holds secrets at the solar system's edge, the history of life bears witness to hidden forces shaping its destiny. The cosmic narrative suggested by Nemesis, Planet 9, and the Shiva hypothesis invites us to imagine a universe in which the boundaries of our solar system are not limits, but thresholds. It is a universe in which unseen companions move slowly through darkness, where distant comets wait in patient silence, and where a single gravitational nudge can set in motion journeys that span millions of years. It is a universe where extinction and renewal, destruction and creativity are inextricably intertwined, and where the edge of space itself is a theatre of subtle but profound influence. Even if Nemesis remains hypothetical, the solar system is not isolated. It is part of a living, dynamic galactic environment, subject to forces both near and far. The icy bodies of the Oort Cloud, the wandering stars and planets, and the deep gravitational rhythms of the galaxy all play a role in shaping the fate of the inner planets, including our own. And within this cosmic dance, Earth is a participant, vulnerable yet enduring, caught between the forces of chance, gravity, and time. Over the past few decades, astronomers have spotted more long-period comets than humanity has ever recorded in all of history. These are comets that take hundreds of thousands, or even millions of years to complete a single journey around the Sun, and until recently, they were largely invisible to us. Thanks to powerful new telescopes, sophisticated sky surveys, and digital tracking techniques, scientists are now beginning to map the origins of these distant wanderers and estimate how often they appear near our planet. Each new comet adds a piece to a vast cosmic puzzle, revealing clues about the farthest reaches of our solar system. At the same time, geologists and paleontologists are turning their gaze inward toward the deep history of Earth itself. They examine layers of rock, sediment, and fossilized remains, searching for evidence of ancient impacts, craters, shocked minerals, or sudden shifts in the fossil record that may have gone unnoticed for centuries. These subtle signs could reveal moments when Earth was struck by celestial objects, perhaps altering the course of life in dramatic ways. Yet some researchers are willing to think even bigger. Certain bold theories suggest that the same distant forces capable of nudging icy objects in the Oort Cloud toward our Sun might also affect the Sun's energy output, or even awaken volcanic fury deep within our planet. In this broader perspective, the great mass extinctions that punctuate Earth's history may not have a single cause at all. Instead, they might result from a convergence of catastrophes, comet showers striking from space, sudden shifts in climate, and violent geological upheavals on land and under the oceans, all occurring within a relatively short span of time. If the so-called Shiva hypothesis is correct, then somewhere in the vast, dark emptiness beyond our vision, the next celestial bombardment could already be lying in wait. Quiet, invisible, and patient, it may one day descend upon Earth, reshaping life once more in ways we can hardly imagine. For many scientists, the Shiva hypothesis remains a topic of intense debate and, for some, deep skepticism. At its heart, the hypothesis proposes a dramatic and unsettling idea that the Earth is periodically threatened by massive cometary bombardments originating from the distant reaches of our solar system, and that these cosmic intrusions are responsible for the mass extinction events that have repeatedly reshaped life on our planet. The theory is named after the Hindu god Shiva, often associated with destruction, and its very name evokes both awe and fear. Yet, despite its dramatic appeal, the scientific community remains cautious, and for very good reasons. One of the primary challenges in evaluating the Shiva hypothesis comes from the Earth's own geological record. Our planet's history is written in layers of rock, sediment, and fossilized life, but that history is far from orderly. Rocks are not permanent. They wear down over time through processes like erosion, weathering, and tectonic activity. Fossils, which might serve as markers of life long vanished, can crumble, dissolve, or disappear entirely. Even entire layers of sediment, which might record the passage of millions of years, can be disrupted or lost. Some layers are buried deep within the Earth, hidden beneath mountains or ocean floors, while others have been shifted, tilted, or inverted by the ceaseless movements of the planet's crust. In such a complex and often damaged record, searching for neat, repeating cycles is an incredibly difficult task. It is like trying to reconstruct a story from a book that has been torn, burned, and scattered across multiple continents. Modern technology has certainly helped, providing tools far beyond what early geologists could imagine. Sophisticated radiometric dating techniques allow scientists to estimate the ages of rocks and fossils with remarkable precision, often within thousands or tens of thousands of years. Satellite imagery and remote sensing give us a global perspective on ancient craters and geological formations. Even so, there remains a considerable amount of uncertainty in pinpointing the exact timing of many extinction events. A few 100,000 years here or there can make a critical difference when attempting to discern patterns spanning tens of millions of years. This inherent imprecision is one reason why many researchers remain cautious about drawing sweeping conclusions. A further difficulty arises from human psychology. Some scientists warn that when people claim to see cycles in mass extinctions, such as events occurring roughly every 26 million or 30 million years, they may be imposing order onto randomness. The human mind is exceptionally adept at pattern recognition, but this talent can also mislead us. Once someone expects a pattern to exist, it becomes all too easy to connect the dots, even when the underlying reality may be chaotic or irregular. In other words, confirmation bias can sneak in, nudging observers to interpret messy geological data in ways that fit a preconceived notion rather than revealing an objective truth. The Shiva hypothesis also depends heavily on a celestial mechanism. The idea that the Oort Cloud, a vast icy shell of comets encasing our solar system, can be periodically shaken, sending comets hurtling toward the inner planets, including Earth. The Oort Cloud is enormous, stretching perhaps a quarter of the way to the nearest star, and its icy inhabitants drift silently in the darkness of space. But what could disturb this immense structure in such a way as to trigger repeated comet showers? Here the hypothesis encounters serious difficulties. One proposed culprit is a hypothetical companion star to the Sun, sometimes referred to as Nemesis. According to the idea, Nemesis would have an elongated orbit taking it far beyond the planets, and its gravitational influence could disturb the Oort Cloud at regular intervals. But no such star has ever been observed, despite decades of increasingly sensitive astronomical surveys. Its existence remains purely speculative, and without direct evidence, the hypothesis loses one of its most dramatic components. Even the Sun itself, as it journeys through the galaxy, moves in a somewhat bobbing motion relative to the plane of the Milky Way. In theory, this oscillation could influence the Oort Cloud, and perhaps trigger cometary incursions. Yet the timing of these galactic movements does not align neatly with the proposed extinction cycles. The peaks and valleys of the Sun's vertical motion through the galactic plane occur on timescales that do not match the supposed intervals of mass extinctions. Without a clear and consistent trigger, the mechanism underlying the Shiva hypothesis remains uncertain and, to many scientists, unconvincing. Another challenge lies in the sheer scarcity of evidence for multiple large-scale comet impacts. Earth has certainly been struck by extraterrestrial objects in the past, some catastrophically, but there is little indication of repeated global-scale impacts occurring in tight clusters every few million years. Today, comets still wander into the inner solar system from time to time, yet even now their numbers are relatively modest. When scientists examine the historical record, using crater counts, ancient sediment layers, and geochemical markers, the evidence for repeated comet showers is far from overwhelming. For many experts, the historical record does not support the claim that Earth has endured periodic waves of mass cometary impacts. Complicating matters further, some of the most devastating mass extinctions appear to have little or nothing to do with impacts at all. Consider the Permian-Triassic extinction, often referred to as the Great Dying, which occurred roughly 252 million years ago. This event was the most catastrophic extinction in Earth's history, wiping out an estimated 90% of marine species and a significant portion of terrestrial life. Yet there is no confirmed impact crater associated with it. Instead, the prevailing explanation centers on massive volcanic eruptions in what is now Siberia. These eruptions, known as the Siberian Traps, released vast quantities of lava, carbon dioxide, and other gases into the atmosphere. The result was a planet-wide climate catastrophe. Temperatures soared, oceans became acidified, and oxygen levels dropped dramatically. In cases like this, comets are unnecessary as an explanation, and including them risks complicating what is already a complex picture. So why, despite these numerous challenges, does the Shiva hypothesis continue to capture attention? Part of the answer lies in human fascination with dramatic, sweeping stories. There is something deeply compelling about the notion that every few tens of millions of years, the cosmos itself might reach out and strike our planet. It is simultaneously terrifying and awe-inspiring, offering the suggestion that life on Earth is entwined with forces far beyond our control. The universe becomes not just a distant backdrop, but an active participant in the history of life, capable of rewriting the rules at regular intervals. For many, the hypothesis provides a simple, elegant explanation for a profoundly complicated problem. Mass extinctions are caused by a bewildering variety of factors: climate change, volcanic eruptions, shifts in ocean chemistry, asteroid or comet impacts, disease, and more. To analyse each extinction event in detail requires untangling countless variables across millions of years. The Shiva hypothesis, in contrast, offers a dramatic single narrative. Periodic comet showers from the Oort Cloud are the overarching driver. It is visually striking, easily communicated in books, documentaries, and headlines, and it resonates with our love for dramatic, almost mythic explanations. Yet even its supporters acknowledge that the theory is far from complete. Many scientists continue to study the hypothesis, not because they are fully convinced, but because certain elements of it are scientifically plausible. It is certainly true that the Oort Cloud exists, and it is theoretically possible for external forces to disturb it, sending comets into the inner solar system. What remains uncertain is the timing, frequency, and actual impact of such events. Even a single confirmed extinction caused by a comet would be enough to demonstrate that the Oort Cloud has influenced life on Earth, providing a tantalizing reason to keep investigating. Interest in the hypothesis is also fueled by the continuing expansion of our knowledge about the outer solar system. Only in recent decades have astronomers begun to map the Oort Cloud in any meaningful way, and the discovery of distant objects beyond Pluto, such as those in the Kuiper Belt and the scattered disk, hints at hidden masses that might interact gravitationally in unexpected ways. As technology improves, we gain new tools to test old ideas. What seemed impossible to verify a few decades ago might soon be measurable with the aid of better telescopes, more accurate orbit tracking, and sophisticated computer models. Mapping long-period comets, those that take tens of thousands or even millions of years to complete a single orbit, could reveal whether they truly arrive in clusters, lending new evidence to the hypothesis or potentially refuting it. There is also a broader historical perspective that encourages scientists to keep an open mind. Many scientific theories that were initially dismissed as wild or implausible eventually proved correct. The theory of continental drift, proposed in the early 20th century, is a prime example. When Alfred Wegener first suggested that continents could move across the Earth's surface, he was widely ridiculed. The idea of entire land masses drifting over geological time sounded absurd. Yet, decades later, accumulating evidence from the ocean floor, plate tectonics, and paleomagnetic studies demonstrated that continents do indeed move. Supporters of the Shiva hypothesis hope for a similar breakthrough. As we uncover more about the distant reaches of our solar system, the missing pieces of the puzzle might finally come together. In recent years, the debate surrounding the Shiva hypothesis has grown more sophisticated. Researchers are no longer simply asking whether comet showers happen, but are instead trying to understand how they would manifest. Would a comet shower strike in a sudden catastrophic burst, bombarding the Earth with multiple impacts over a few decades or centuries? Or would it occur as a slow drizzle, with impacts spread over thousands of years, each individually less dramatic but collectively significant? Scientists are also searching for chemical clues in ancient rocks. Certain elements, such as iridium, are rare on Earth, but abundant in extraterrestrial objects. Spikes in these elements could serve as fingerprints of past impacts. Matching these geochemical signals with the timing of extinction events is a major focus of current research. Another area of active study involves creating more realistic models of the Oort Cloud itself. Previously, the cloud was treated as a static shell, largely unaffected by the galaxy around it. Modern simulations, however, take into account the gravitational influence of passing stars, molecular clouds, and even the subtle tug of the Milky Way's spiral arms. By understanding how the cloud reacts to external forces, scientists can better predict when and how it might be shaken enough to send comets hurtling inward. Future space missions and sky surveys are expected to dramatically increase the number of long-period comets we can track, providing a richer dataset to test these models. Despite all these efforts, the Shiva hypothesis remains in a precarious position. It is neither widely accepted nor entirely dismissed. Some scientists push it forward, refining models, searching for patterns, and exploring the outer solar system, always hoping that one day a compelling piece of evidence will emerge. Others remain skeptical, emphasizing the importance of rigorous data, clear mechanisms, and reproducible evidence. For now, the theory occupies a liminal space, suspended between possibility and speculation. The continued interest in the Shiva hypothesis underscores the larger human fascination with the unknown. It illustrates our desire to link ourselves to the broader cosmos, to find meaning and narrative in the vast, often indifferent universe. It also highlights the careful balance in science between imagination and evidence. While the idea of periodic cometary impacts is tantalizing, it is the painstaking work of observation, analysis, and model building that will ultimately determine its validity. The debate is as much about methodology as it is about the cosmos. How do we interpret the fragmented and imperfect record of Earth's past? How do we separate true patterns from the illusions created by chance or bias? And how do we reconcile dramatic, intuitive explanations with the slow, incremental accumulation of evidence? The Shiva hypothesis sits at the intersection of these questions, offering both an inspiring narrative and a rigorous challenge. It is a fact that science is not a static collection of facts, but a dynamic, ongoing process. Ideas rise, fall, and evolve. The Earth's history is vast and complex, and our understanding of it continues to grow, shaped by new observations, technologies, and insights. The Shiva hypothesis, with all its uncertainties and possibilities, is part of this unfolding story. A story that stretches from the icy reaches of the Oort Cloud to the extinction events that have punctuated life on our planet, and ultimately to our ongoing quest to understand our place in the cosmos. Even as the evidence remains inconclusive, the hypothesis continues to inspire research, debate, and imagination. It encourages scientists to ask difficult questions, to develop better models of cometary dynamics, and to scrutinize the geologic record with fresh eyes. In doing so, it keeps alive the possibility that one day we might discover that the distant Oort Cloud has indeed left its mark on Earth's history, that celestial events have helped shape the course of life itself, and that the cosmos is a far more active participant in our story than we have yet fully realized. For now, the Shiva hypothesis remains a mixture of caution, curiosity, and cosmic wonder. It is a testament to human imagination and scientific rigor alike, reminding us that even in the face of uncertainty, the quest to understand the universe continues unabated. It also speaks to a fundamental human desire to see ourselves as part of a larger interconnected story, a narrative that spans both space and time, from the icy outskirts of the solar system to the very core of a life on Earth. The debate will continue, as will the search for answers, because understanding our past and the forces that have shaped it is inseparable from understanding our future. In the late 1970s, humanity attempted something bold, something that had never been done before. 2 spacecraft were built, small compared to the vastness of space, but mighty in purpose. These were the Voyagers. They were designed and constructed with a mission unlike any other: to leave the safety of Earth, to journey beyond the familiar orbits of our neighbouring planets, and to show us what lay in the farthest reaches of the solar system. The adventure began with Voyager 2, which was launched in the month of August in the year 1977. Only a few weeks later, Voyager 1 followed. It is interesting that Voyager 2 was launched first, even though the numbering might suggest otherwise. But the paths they would take through the solar system required that order. Their mission was daring and ambitious. These spacecraft were sent to explore the great giants of our solar system: Jupiter, Saturn, Uranus, and Neptune. Worlds so massive and distant that for centuries they had been little more than faint points of light in the sky, seen only through telescopes. The Voyagers were to visit them up close, to look at their swirling clouds, their mysterious rings, their countless moons, and to send back pictures and data that no human eye had ever witnessed before. At the time of their construction, no one knew how long these delicate machines would survive. The environment of outer space is harsh. There is freezing cold, dangerous radiation, and no one to repair them if something went wrong. Yet the engineers who built the Voyagers gave them incredible resilience. Their design was sturdy, their instruments carefully shielded, and their systems built with backups upon backups. No one dared to imagine they would last for decades. And yet, here we are, nearly half a century later, and both spacecraft are still alive, still sending whispers of information back to Earth. Over time, the Voyagers became more than spacecraft. They became symbols. They stood for human courage, for curiosity, for our deep desire to know what lies beyond the horizon. They became reminders that even though we are tiny creatures living on a small planet, orbiting a medium-sized star, we still have the daring to send pieces of ourselves into the unknown. Of the two, Voyager 1 has become the most famous. Today, it holds a record no other human-made object can claim. It is the farthest object ever sent by our species. It has travelled farther than the Moon, farther than Mars or Jupiter, farther even than Pluto, the tiny icy world once considered the 9th planet. In the year 1990, Voyager 1 passed the orbit of Pluto. At that time, astronomers believed this marked the very outer edge of the solar system. In truth, we now know that the solar system extends far beyond Pluto, but Voyager 1 had crossed what people once thought of as the final frontier. Then, in the year 2012, Voyager 1 achieved something even greater. According to the space agency NASA, the spacecraft crossed into interstellar space. This means it passed a boundary called the heliopause, the invisible border where the influence of our sun ends and the power of the galaxy begins. Inside the heliopause, the sun's solar wind, streams of charged particles it constantly emits, pushes against the thin gas between the stars. Beyond it, the sun's reach weakens, and the interstellar medium dominates. Voyager 1 was the first human creation to cross this line. To understand its distance, we must first explain a measurement astronomers use, the astronomical unit, or AU. One astronomical unit is the distance between the Earth and the Sun. That distance is about 93 million miles, or roughly 150 million kilometers. It is a vast distance, yet it is just the first step in the ladder of cosmic measurement. Voyager 1 is now more than 160 astronomical units away from the Sun. That is over 15 billion miles, or about 24 billion kilometers. And yet, even at that enormous distance, it has not reached the fabled Oort Cloud, the icy shell of comets and frozen fragments that marks the Sun's farthest domain. In fact, astronomers believe Voyager 1 is still only 3 to 8% of the way to the inner edge of that cloud. This is important to remember. After nearly 50 years of continuous travel, after flying farther than any spacecraft in history, Voyager 1 has not even reached the doorstep of the Oort Cloud, and the Oort Cloud itself is staggeringly large. Its outer boundary may lie as far as 100,000 astronomical units from the Sun. To reach even halfway there, Voyager 1 would need to keep flying for tens of thousands of years, and even then, it would just be a tiny dot moving in an endless sea of ice and rock. Trailing behind its sibling is Voyager 2, which followed a slightly different path. Its journey allowed it to perform something Voyager 1 did not: flybys of both Uranus and Neptune. This made Voyager 2 the first, and still the only, spacecraft to visit those two distant planets up close. It revealed Uranus's strange tilted axis, its faint rings, and its moons. At Neptune, it showed us the giant dark storm swirling in its atmosphere and the icy surface of its moon Triton, where geysers of nitrogen gas erupt into space. Voyager 2 continues outward, though at a slightly different angle. It still communicates with Earth, though like its twin, many of its instruments have been shut down to save energy. It moves at around 15 kilometers per second, a speed that sounds swift, but in cosmic terms is actually quite slow. Like Voyager 1, it will never come close to reaching the Oort Cloud before its power fades completely. Another spacecraft launched many years later also tried to push the boundaries of exploration. This was New Horizons, launched in the year 2006. Unlike the Voyagers, which were designed for grand tours of multiple planets, New Horizons was built with a specific mission to reach Pluto, the mysterious dwarf planet at the edge of the planetary system. New Horizons was the fastest spacecraft ever launched at that time. It sped away from Earth so quickly that it took less than 10 years to reach Pluto, arriving in the summer of 2015. There, it sent back stunning images of icy mountains, frozen plains, and a heart-shaped region on Pluto's surface that instantly captured the world's imagination. After Pluto, New Horizons did not stop. It kept going into the Kuiper Belt, a region filled with icy bodies and dwarf planets. In the year 2019, it performed a flyby of a small object called Arakoth, which orbits about 44 astronomical units from the Sun. This was farther than Neptune, yet still nowhere close to the Oort Cloud. New Horizons continues to operate and is expected to remain active until around the year 2040. By that time, it may reach a few hundred astronomical units from the Sun. This is an astonishing achievement, yet even that enormous distance is only a fraction of the way to the Oort Cloud's edge. All three spacecraft, Voyager 1, Voyager 2 and New Horizons, are travelling outward, drifting in the general direction of the Oort Cloud, yet none of them were designed to reach it. The truth is, with today's technology, the Oort Cloud is unreachable. Every picture you have ever seen of it is an artist's imagination. Every diagram is a model. We cannot see it directly. It exists in theory, supported by evidence, but remains unseen. To understand just how far it is, think of light, the fastest thing in the universe. Light from the Sun takes about 8 minutes to reach Earth. To travel to Pluto, it takes about 5 hours, but to reach the inner edge of the Oort Cloud, light would need nearly 1 full month. To reach the outer edge, it would take over a year. Our spacecraft are much, much slower than light. At their present speeds, they would need tens of thousands of years to cross even part of the Oort Cloud. This means that for now, it lies forever beyond our reach. And yet, scientists dream. Some propose radical new propulsion methods, using powerful lasers to push tiny spacecraft, or using fusion engines, or even concepts like antimatter propulsion. With such ideas, perhaps a probe could reach the Oort Cloud in a few hundred years instead of tens of thousands. Still, these are ideas that exist only on paper. No working prototype has been built. Even if we could design such a mission, it would not be like the space missions we know today. It would span multiple human lifetimes. The people who designed it would not live to see its success. Funding and planning such a project would be unimaginably difficult. For now, it remains a dream for future generations. Even if we cannot send spacecraft there, we may still learn about the Oort Cloud in other ways. With powerful telescopes like the James Webb Space Telescope, and with upcoming survey instruments, astronomers may discover more distant icy objects that give us hints about the Oort Cloud structure. Each discovery helps us refine our theories and imagine how we might one day explore it. The Oort Cloud also matters for another reason. It may be the bridge between the Sun and the galaxy. Our solar system is not alone. It is just one star among hundreds of billions in the Milky Way. Beyond the Sun's reach lies interstellar space. In this larger view, the Oort Cloud is not just the edge of our system. It is the threshold to the stars. So for now, the Oort Cloud waits, hidden, silent, mysterious. It has not yet been touched by any spacecraft, and it may not be for many generations. But it is there, surrounding us like a faint halo, holding the icy relics of our solar system's birth. One day, perhaps, humans will build ships strong enough and fast enough to reach it. When that day comes, we will finally see what has only been imagined. Until then, we must wait, and we must dream. The Voyagers, New Horizons, and all the spacecraft we have launched so far are like scouts, venturing into the unknown, paving the way for the distant future. Astronomy, the ancient science of watching the skies, does not always progress in neat little steps, like footprints evenly spaced in sand. Often, it moves forward in great leaps, surprising us with discoveries that once seemed impossible. Ideas that once belonged only to stories and science fiction novels have, time and again, become proven facts that reshape our understanding of the universe. Not so long ago, within the lifetime of many people still alive today, the thought of seeing planets around other stars seemed like nothing more than wild imagination. For centuries, astronomers wondered, could there be other worlds like Earth circling suns far away? Writers dreamed about them, and philosophers speculated, but most scientists considered the idea unproven and unprovable. Yet now, in the early 21st century, we know of thousands of such planets, called exoplanets, and we discover more every single year. The same transformation has happened with black holes. For much of the 20th century, they were treated as strange mathematical curiosities, whispered about in equations and thought experiments. They were the monsters of Einstein's theory, so dense that nothing, not even light, could escape them. But were they real, or just ghostly illusions produced by mathematics? Now we know without doubt that they exist. Not only have we detected their pull on nearby stars and gas, but we have also captured the very first photograph of a black hole's shadow, an image that shook the world in the year 2019. And yet, as one mystery is solved, another rises. Hanging over modern astronomy like a distant challenge is the question of the Oort Cloud. For decades, scientists have believed that this enormous invisible halo of icy bodies surrounds our solar system, stretching perhaps halfway to the stars. But can we ever see it directly? Can we go beyond theory, beyond educated guesses, and finally bring it into the light of observation? The challenge is immense. Sending a spacecraft all the way out to the Oort Cloud is still far beyond our reach. The distances are staggering. If Earth were reduced to the size of a single marble, the Oort Cloud would begin several football fields away. A spacecraft travelling as fast as the Voyagers, those brave machines launched in the 1970s, would still take thousands of years to get there. So we must be clever. If we cannot travel to the Oort Cloud, we must learn to sense it from afar. We must use the tools we already have: light, gravity, and the delicate art of shadows. We must train ourselves to see the universe with new eyes, sensitive to signals that ordinary vision cannot detect. One of the most promising paths lies in infrared astronomy. The objects of the Oort Cloud are icy and cold, frozen remnants left over from the dawn of the solar system more than 4.5 billion years ago. But they are not completely frozen into silence. They are not at absolute zero, the coldest temperature possible. Instead, they emit the faintest traces of heat, far too dim for human eyes or even for ordinary optical telescopes, but just enough to be seen in the infrared spectrum, which is sensitive to warmth. This is where our great observatories come in. NASA's Spitzer Space Telescope, the European Space Agency's Herschel Observatory, and the magnificent James Webb Space Telescope launched in the year 2021 have opened entirely new windows into the universe. These machines can see the faint glow of brown dwarfs, failed stars that never ignited. They can find lonely planets drifting through space without a parent star. They can peer into the dusty cradles where new stars are born. But finding the Oort Cloud is far harder. Its members are tiny compared to planets, scattered across unimaginable distances and radiating almost no heat. Even James Webb, with its giant golden mirror and unmatched sensitivity, would likely not be able to see a single Oort Cloud object on its own. And yet, there is hope. If trillions of these icy bodies exist, each sending out the weakest whisper of warmth, then together they might form a faint infrared glow, a background emission that surrounds the solar system like a ghostly halo. By carefully subtracting all other known sources of infrared light, stars, galaxies, dust within our own system, astronomers might reveal the faint leftover signal of the Oort Cloud itself. It would not be a picture of individual comets, but a kind of fingerprint left by the population as a whole. A whisper, made audible by the chorus of countless icy voices. But light is not our only tool. Sometimes it is the absence of light that reveals hidden things. This is the principle of occultation. When a small, unseen object passes in front of a distant star, it blocks a tiny fraction of the star's light. The star seems to dim, just for an instant, and then shine again. These flickers are brief, sometimes lasting only a fraction of a second. But if they are carefully recorded, they can reveal astonishing secrets. Occultations have already exposed faint rings around distant worlds, discovered new moons, and mapped objects in the Kuiper belt beyond Neptune. Applying this technique to the Oort Cloud is much more challenging. The stars must be observed continuously across huge swathes of the sky with extreme precision. The dimming caused by an Oort Cloud body would be so small and so brief that only the most advanced surveys could hope to notice it. But with enough patience and enough stars watched, it could be done. The Vera Rubin Observatory, soon to begin full operations, may play a key role. Its wide-field telescope will scan the sky with breathtaking speed and accuracy, building up a movie-like record of the heavens. If a single Oort Cloud object drifts across a star, Rubin may catch the event, and if several telescopes spread far apart on Earth or even in space record the same flicker, then astronomers could calculate the object's distance, size, speed, and path. One such detection would be historic. Repeated detections could allow us to begin mapping the invisible kingdom of the Oort Cloud piece by piece. There is another way to sense what cannot be seen, a way that relies not on blocking light but on bending it. This is the method of gravitational microlensing. According to Einstein's theory of relativity, gravity is not just a force, it bends space itself. Light travelling near a massive object follows this curve, much as a river bends around a rock. The result is that a distant star can appear warped, magnified, or brightened if another object passes between it and us. Astronomers usually use microlensing to detect exoplanets, or even dark objects like black holes. But in principle, it could also reveal large Oort Cloud bodies, perhaps even hidden dwarf planets or rogue wanderers that drift on the edge of our system. Imagine a star far away brightens slightly and briefly, not because it changed, but because some invisible traveller in our own neighbourhood bent its light. That flicker would be a cosmic fingerprint of something real, something massive, lurking in the dark. Some scientists have imagined more daring methods. Instead of waiting passively, they propose sending swarms of small spacecraft into the outer solar system. These machines would not need to travel all the way to the Oort Cloud. Instead, they could linger beyond Neptune and Pluto, equipped with sensitive instruments, waiting like hunters in the shadows. If one probe were nudged by a faint gravitational tug, or struck by the tiniest icy fragment, it could provide the first close evidence of an Oort Cloud body. With many probes spread across a wide area, the chances of such encounters would increase. It would be like casting a net in the ocean, not knowing what strange creatures might drift into its threads, but confident that eventually something will. The greatest obstacle in studying the Oort Cloud is not only its distance but its silence. The objects there are small, they move slowly, they reflect little sunlight and emit almost no heat. They do not send out radio waves or magnetic fields. They are like cosmic shadows, present but almost invisible. Here is where modern technology, especially artificial intelligence, may help. Sky surveys today produce unimaginable oceans of data, far more than any team of humans could ever examine. Hidden in those records might already be the subtle signals of Oort Cloud objects, tiny dips in starlight, faint motions, almost imperceptible irregularities. AI trained to recognize such patterns could one day find them, flagging the telltale signs that human eyes would miss. What once seemed impossible, sifting through billions of stars for millisecond flickers, may soon become routine for machines built to see what we cannot. Some ideas sound like science fiction, but are not impossible. Concepts like solar sails pushed forward by sunlight itself, or ultralight probes driven by powerful lasers, could one day make journeys toward the outer solar system far faster than anything we have now. Projects like Breakthrough Starshot already dream of sending tiny spacecraft to the nearest stars. But the same technology could be used closer to home. Even if such probes reached only a fraction of the distance to the Oort Cloud within a human lifetime, they could serve as scouts, observing, listening, sampling, and perhaps sending back the first direct evidence of the mysterious cloud. Imagine a grain-sized spacecraft, no heavier than a feather, racing outward on beams of light, quietly reporting back on the unknown frontier of our solar system. Imagine for a moment that people could reach out into the frozen darkness at the very outer edge of our solar system and bring back even the tiniest piece of the Oort Cloud. Picture holding in your hands a fragment of that distant, mysterious region where countless icy objects drift silently, far beyond the orbit of Neptune, beyond the planets we know so well, and nearly at the point where our solar system fades into the endless space between stars. Such a discovery would not just be an achievement of engineering or exploration. It could completely change the way we understand the story of the solar system, how the planets formed, and even the origins of life itself. Long before the Earth became a blue and green world full of life, before the moon settled into its familiar orbit, and even before the giant planets, Jupiter, Saturn, Uranus, and Neptune took shape, the solar system was a place of chaos and creation. Rocks collided, combined, or broke apart. Clouds of dust swirled in huge invisible currents, and the earliest materials of our planetary neighbourhood came together and separated under the force of gravity. In the middle of this chaos, countless small icy objects were thrown outward, carried far from the sun's warmth by the gravitational pull of the growing planets. They drifted into the cold, silent distance, forming a vast, thin shell around our solar system that we now call the Oort Cloud. It is a place almost completely unseen, made of objects maybe only a few kilometres across, each one like a time capsule holding the original materials from which the solar system was born. The idea of bringing back a piece from this distant frozen edge is staggering. To try such a mission would be to go on a journey unlike any in human history. The spacecraft would have to travel tens of thousands of astronomical units, which means tens of thousands of times the distance from the Earth to the Sun. It would need to find an object maybe no bigger than a small mountain, land on its icy surface, collect a sample, and then return across that enormous distance to deliver the material safely back to Earth. The technical problems are huge, yet humanity has already made steps along this path. Japan's Hayabusa missions, for example, successfully brought back samples from the asteroids Itokawa and Ryugu. NASA's OSIRIS-REx spacecraft went to the near-Earth asteroid Bennu, collecting a large amount of material for study. These missions, however, focused on targets fairly close to Earth, within the inner solar system. The Oort Cloud, by contrast, is a remote frontier that stretches halfway to the nearest stars. A mission there would need technology, patience, and precision on a scale never tried before. To face these challenges, scientists and engineers are looking at new possibilities. Advanced engines could one day make the journey possible. Ion drives, which use electric fields to push ions and provide continuous but gentle thrust over years or decades, offer one possible method. Nuclear-powered engines, which deliver huge amounts of energy over long periods, could provide the power needed for steady acceleration across the distance between stars. Some ideas even suggest using solar or laser sails, thin, shiny surfaces pushed by the pressure of light itself, to carry a spacecraft on a journey that could take decades or even centuries. For now, though, the most practical way is to study comets that come from the Oort Cloud, rather than going there directly. Even these brief visitors give amazing opportunities. When a comet drifts inward from the outer edges, its icy surface starts to heat under the sun's warmth. Gas and dust are released, forming the beautiful tails we see in these celestial travellers. Scientists can study this material both from Earth and from spacecraft that pass close to the comets. The Stardust mission, launched by NASA in the late 20th century, collected dust from the coma of Comet Wild 2, bringing tiny grains back to Earth for detailed lab analysis. Although Wild 2 is not thought to have come from the Oort Cloud, the mission showed what is possible. Careful collection and study of ancient material, revealing the chemical makeup of objects formed billions of years ago. A future mission could use these methods on a true Oort Cloud comet, giving humanity a direct look at the farthest parts of our solar system, or even landing on such an object to take samples directly from its icy surface. The scientific value of a real Oort Cloud sample is almost beyond imagination. First, it could show the basic building blocks of the solar system. The ice, dust, and rock in these objects may hold the same elements and molecules found in the original cloud of gas and dust from which the sun and planets formed. Some of this material could have stayed almost unchanged for more than 4.5 billion years, giving an unmatched window into the chemical environment of the early solar system. By studying these materials, scientists could learn where the solar system formed, how it collected the ingredients that later formed planets, and what the early conditions were like before life appeared on Earth. There is also an idea that Oort Cloud objects may have helped bring water and organic molecules to our young planet. Early Earth was a violent, molten world, shaped by constant impacts from space. Volcanoes raged across the surface, and the atmosphere was likely thin and dangerous for life. Over time, comets and asteroids hit the planet, bringing water ice and carbon-based compounds. If even some of these icy bodies came from the Oort Cloud, they could have helped form Earth's oceans. Moreover, if these comets carried organic molecules like amino acids, alcohols, or other carbon compounds, they might have provided the raw material needed for life to start. A returned sample could show the exact makeup of these icy visitors, possibly proving whether Earth's life-giving ingredients came from the distant frozen regions beyond Neptune. Some scientists think even further, guessing that fragments of the Oort Cloud might hold material from other stars. As the Sun moves through the galaxy, it interacts with other stars, and it is possible that the Oort Cloud has captured objects from beyond our solar system. A returned sample could contain isotopes that do not match those from the Sun, or minerals formed under conditions completely different from our own planetary neighbourhood. In this way, a piece of the Oort Cloud would not only tell the story of our solar system, but could also be a tiny record of the galaxy itself. Perhaps hidden in its icy structure could be complex organic molecules, pre-life compounds similar to the building blocks of RNA or DNA. While these molecules would not prove that life started there, their presence would strongly suggest that the chemical ingredients for life are common in space, forming naturally even in the cold and dark. If these ingredients are widespread, it raises the exciting possibility that life itself may exist in many places across the universe. The responsibility of returning such a sample safely to Earth is enormous. How do we make sure it is not contaminated by Earth materials, and that it does not bring unknown substances to our planet? Missions like Stardust and OSIRIS-REx have pioneered ways to handle fragile space material, using airtight containers, working in ultra-clean labs, and relying on teams of highly trained scientists. A true Oort Cloud sample would need even stricter precautions. Analysis would probably be slow and careful, maybe done in steps. Parts of the sample could be shared with labs worldwide so scientists can study it in many ways, while other parts could be saved for future generations, possibly using technologies not yet invented. The goal would be to gain as much knowledge as possible while minimizing any risk. History shows that returned samples often have surprises. The Stardust mission, for example, brought back minerals that had formed at extremely high temperatures, an amazing discovery since it went to a cold, distant comet. This unexpected result made scientists rethink models of how material moves in a solar system, showing that matter from the inner regions could travel outward and mix with distant, colder material. A sample from the Oort Cloud could similarly challenge our assumptions, questioning long-held ideas about how planets form, how matter moves, and how the solar system chemically evolved. It could force us to rewrite textbooks, rethink theories, and create new models of how solar systems, and perhaps even life, develop. The idea of opening a sealed container with material that has not seen sunlight since the start of the solar system is deeply moving. It is almost like listening to a whisper from the edge of time. To hold a piece of ice and dust that has drifted for billions of years, untouched and unchanged, would be to connect directly with the earliest moments of our cosmic neighbourhood. It is a physical link to a time long before Earth existed, long before the planets formed, and perhaps even before our sun fully shone. The experience would be more than scientific. It would be almost spiritual, giving humanity a chance to touch a piece of its own cosmic history. Picture the spacecraft that might carry out this mission. It would leave Earth on a carefully planned path, likely taking years, maybe even decades, to reach the farthest regions of the solar system. Along the way, it would need to navigate the subtle gravitational pulls of the giant planets, adjust its course with extreme care, and survive the harsh conditions of space, including cosmic radiation and extreme cold. Upon reaching the Oort Cloud, it would face the delicate task of finding a suitable target, an object only a few kilometers across, blending into the darkness of a nearly lightless region. Landing or even hovering near such an object would need precision at a level almost unimaginable, requiring automated systems capable of real-time adjustments across vast distances. Once a sample is collected, the journey back would begin. The spacecraft would need to accelerate slowly, carrying its precious cargo toward the inner solar system. Even small mistakes could lead to failure, so every move would be planned and carried out with great care. When it finally reaches Earth, the spacecraft would need to protect the sample from heat, contamination, and mechanical stress during re-entry and landing. Scientists would then begin the careful process of studying the material, uncovering its secrets one layer at a time. The rewards, however, could be enormous. Scientists could learn the exact makeup of ancient ices, revealing the original mix of water, carbon compounds, and other elements in the young solar system. They might find clues about how planets moved, how water and organic materials arrived on Earth, or even how our solar system interacted with nearby stars. Every grain of dust, every molecule of ice could tell a story, helping us understand not only how our solar system formed, but also how similar processes might happen around other stars. Moreover, the mission could inspire generations of scientists, engineers, and dreamers. The idea of going to the edge of the solar system to bring back material that has travelled through space for billions of years captures the imagination. It speaks to people's desire to explore, understand, and reach beyond the limits of everyday life. It reminds us that curiosity and determination can overcome even the hardest challenges, and that the rewards of exploration are not just knowledge but also wonder. Even if the mission is not launched for many decades, the work being done today is essential. Scientists are studying comets from the Oort Cloud as they pass through the inner solar system, developing technologies for long missions, and designing instruments that can study fragile materials with extreme precision. Every small step, each comet observed, each experiment done, brings us closer to the day when people might finally reach out and bring back a piece of that distant icy edge. It is also worth imagining the moment of discovery. A scientist carefully opens the container in a clean lab, revealing grains of ice and dust that have stayed unchanged for more than 4.5 billion years. Microscopes show structures never seen on Earth. Chemical tests reveal compounds older than our planet. Isotope measurements suggest links to parts of space far beyond the sun's reach. In that instant, the past comes alive. We see the solar system as it once was, raw and unformed, and we glimpse the ingredients from which planets, oceans, and maybe life itself arose. Such a mission would not only be about science, it would be about connection. It would remind us that we are part of a huge ancient universe, that Earth and humanity are linked with billions of objects drifting silently in the dark, and that the universe holds more secrets than we can imagine. A sample from the Oort Cloud would be a gift from the distant past, a message written in ice and dust, carrying memories from long before Earth existed, and perhaps offering clues about how common, or rare, life might be across the galaxy. In the end, the dream of bringing back a piece of the Oort Cloud is both bold and deeply human. It combines our technical skill with our endless curiosity, our desire to explore with our need to understand. It challenges our ability to imagine the unimaginable, to plan journeys lasting decades, and to think on the scale of the solar system itself. And yet, despite the huge challenges, pursuing such a mission reflects our most basic qualities: curiosity, creativity, and the drive to reach beyond the familiar to touch the unknown. Perhaps, in the not-too-distant future, humanity will succeed. Perhaps one day we will hold in our hands a fragment of ice and dust that has drifted for billions of years in the frozen darkness at the edge of the solar system. It will be quiet, unassuming, and yet it will tell us much. A whisper from the earliest days of the sun, a messenger from the distant reaches beyond Neptune, and a reminder that the universe is far bigger and more mysterious than we have fully understood. That fragment could tell us where we came from, how our solar system formed, and perhaps even how life began. It would be a treasure beyond measure, a bridge to the past and proof of the human spirit of discovery. Holding such a fragment would connect us not only with the Oort Cloud, but also with the story of humanity itself, the story of a species that dared to look up, to wonder, to travel across unimaginable distances, and to seek knowledge in places untouched since the dawn of time. It is a story that continues today and will continue for generations, inspired by the vision of reaching the frozen edge of our solar system and bringing home a piece of its ancient, silent heart. And so, the dream stays alive. Scientists, engineers, and dreamers keep studying, planning, and inventing, turning what was once imagination into a real goal. The Oort Cloud waits, drifting silently at the limits of the sun's influence, holding secrets from the earliest days of the solar system. One day, humanity may go to that distant frontier, take a piece of its icy mysteries, and return to Earth with a story written in the language of dust and ice. A story waiting more than 4 billion years to be told. To imagine the day we finally open that first container from the Oort Cloud is to imagine a moment of awe and wonder unlike any other. It reminds us that the universe is vast, full of mysteries, and waiting for those brave enough to seek them. It promises discovery, knowledge, and perhaps even answers to long-asked questions. Where did we come from? How did our world form? And what possibilities lie beyond our solar system? In that small, silent, ancient fragment, we may find not only a window to the past, but also a guide for the future, inspiring generations of explorers yet to come. Stars are not born in isolation. They are born together in families, in large groups inside dense clouds of gas and dust. These clouds are like cosmic wombs, holding within them the seeds of many suns. Gravity slowly pulls the material together, squeezing and compressing until at last a star begins to burn at its heart. Yet the star is never truly alone. Around each newborn star, a flat spinning disk of material forms, whirling like a cosmic carousel. This disk is made of gas, ice, and dust, and it is from this material that entire worlds are sculpted. Planets, moons, asteroids, and comets all emerge from this swirling nursery. Over millions of years, pieces collide, merge, and grow into worlds. Some of these worlds stay close to the star, others are tossed outward into distant orbits, while still others are cast away entirely, thrown into the emptiness between the stars. Our own sun was born this way about 4.5 billion years ago, and what happened around it is most likely happening around countless other stars as well. We know that giant planets such as Jupiter act as cosmic slingshots. They can hurl comets and smaller bodies outward into the farthest reaches of a star's gravitational pull. In our own solar system, this process is thought to have created a vast halo of icy leftovers that surrounds us even now, the Oort Cloud. If that is true here, then it is almost certainly true elsewhere. All across the galaxy, the night sky may be filled with stars that are not only orbited by planets, but are also wrapped in invisible halos of frozen debris, each with its own Oort Cloud. But here is the problem. Even though astronomers believe our solar system has its own Oort Cloud, we have never directly seen it. The objects are so small, so dark, and so distant that they remain hidden. If we cannot see our own cloud, how could we possibly hope to see one around another star, perhaps hundreds or even thousands of light years away? Still, scientists are imaginative people. They do not give up easily. If they cannot see the clouds directly, they try to think of clever ways to spot their effects instead. One idea is to look for unusual comets in other star systems. Imagine watching a distant star for a very long time. Suddenly a strange comet might appear, falling inward toward the star from some distant, unseen reservoir. If our instruments were sharp enough, we could detect the faint trail it leaves behind. Or perhaps, as the comet passes in front of the star, it might block a tiny portion of the starlight, causing the star to dim for a short while. This is similar to the way we detect exoplanets, by observing tiny dips in brightness when a planet crosses in front of its star. The challenge is that these events are rare and unpredictable. A comet does not announce itself ahead of time. It simply appears, races by, and is gone. To catch such an event, astronomers would need years of patient watching and very good luck. Another approach involves using infrared telescopes. When icy bodies in the far outer regions of a star system absorb starlight, they re-emit that energy as heat. The glow is faint, but in theory, a powerful telescope can detect it. Astronomers have already used this method to find dusty disks around young stars, disks that are warmer and closer to the star, where planets are still in the process of forming. But in a few cases, older stars have also been found with colder, more distant disks. These are not the glowing birthplaces of planets, but instead something farther out, quieter and more mysterious. They may be the analogues of the Kuiper belt in our own system, or even precursors to Oort clouds themselves. One of the most famous examples is the star Vega. Vega is one of the brightest stars in our night sky, often called the jewel of the summer skies in the northern hemisphere. Infrared observations of Vega revealed a faint ring of dust and ice stretching far beyond its known planets. The structure extended much farther out than expected, almost as if the star had a ghostly halo of leftovers still drifting in space. Vega is not alone. Other stars such as Fomalhaut and Beta Pictoris show similar signs. Around them, astronomers have detected faint rings or disks of material at great distances from the star. These could very well be the early hints of Oort-like structures forming around alien suns. While this is not proof, it is suggestive. The universe rarely gives away its secrets easily, but sometimes it leaves tantalizing clues. Another method to search for alien Oort clouds is to look directly for comets as they fall inward. Just like in our solar system, icy bodies around other stars should occasionally be disturbed and pulled toward the inner regions. As they approach the star, the heat causes their frozen surfaces to vaporize, releasing gas and dust. This creates the beautiful glowing tails that make comets so striking. If such a comet were to pass in front of its star, the light we see from that star would change in subtle ways. It might dim slightly, or its spectrum, the breakdown of light into colors, might reveal unusual fingerprints of gas and dust. Astronomers call this phenomenon spectral dimming. Remarkably, a few of these exocomets have already been spotted. Once again, Beta Pictoris stands out as a fascinating case. This star has been watched carefully for many years, and astronomers have observed sudden, brief dips in its light. These dips do not match the behavior of planets. Instead, they appear to come from small, dusty objects moving on chaotic, unpredictable orbits. The best explanation is that they are comets plunging inward from some distant reservoir of icy debris, perhaps the very edge of an alien Oort cloud. If this interpretation is correct, then we may already have glimpses of other stars' Oort clouds in action. But there are limits. Unlike the comets in our own solar system, which we can track across the sky for weeks or months, exocomets are much harder to follow. They appear as faint, fleeting signals, often lasting only hours or days. We cannot yet map their orbits or know exactly where they came from. All we are left with are fragments of evidence, brief shadows of something much larger and more complex. Why should we care about Oort clouds around other stars? The answer is that they could teach us a great deal about how planetary systems form and evolve. If Oort clouds are a natural part of stellar life, then they are not rare oddities but expected features of almost every star. By studying them, we could learn how large they are, how many comets they contain, and how much icy material lingers in the outskirts of solar systems. We could also compare different systems to see whether our own Oort cloud is typical or unusual. This knowledge might even help us answer big questions about the history of Earth itself. Comets are thought to have played a role in delivering water and organic molecules to the young Earth, possibly contributing to the origins of life. At the same time, comet impacts may have caused mass extinctions. If Oort clouds exist everywhere, then comet-driven events may be a universal feature of planetary history. Life across the galaxy could be shaped, again and again, by icy wanderers from the dark edges of space. Every so often, stars pass close to one another in their slow dance through the galaxy. When this happens, the gravitational tug of one star can disturb the Oort cloud of another. Suddenly a burst of comets may be sent inward, creating a storm of impacts. If astronomers were watching at just the right moment with sensitive telescopes, they might detect a sudden spike in comet activity around a distant star. Such an observation would be rare, but it could serve as striking evidence that alien Oort clouds are real. There is also a bolder idea. Some scientists suggest that we might one day detect rogue comets that were born in the Oort cloud of another star, only to be flung into interstellar space millions of years ago. These would be true wanderers between the stars. In fact, we may already have seen examples. In the year 2017, astronomers spotted a strange object passing through our solar system. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It came racing in from interstellar space and then vanished again, never to return. Later, in the year 2019, another interstellar visitor was spotted, this time unmistakably a comet, called Borisov. These discoveries show that comets and debris do indeed travel between the stars. If we could catch such objects and study their chemical fingerprints, We might even be able to tell which star system they came from. Differences in water content, unusual elements, or rare compounds could reveal a birthplace far beyond our own sun. To do this properly, we would need either very fast probes capable of chasing down such visitors, or incredibly powerful telescopes that can analyze their light in fine detail. The technology is not here yet, but the possibility hangs before us like a promise. The idea that every star in the night sky may be surrounded by its own cold, distant halo of icy bodies changes how we think of the universe. These halos are not bright, not dramatic, but they are enduring. They are the frozen relics of creation, silent archives of a system's earliest days. If they are as common as many scientists suspect, then the galaxy is richer than it appears. Around every sun, whether near or far, quiet armies of comets may circle, waiting in the dark. They may be the most common leftovers in the universe, hidden borders that mark the outer edges of stellar kingdoms. Somewhere out there, in the great star fields, frozen worlds are circling suns we cannot see with the naked eye. They drift patiently, untouched for billions of years, until one is nudged, disturbed, and sent inward on a fiery plunge. And just as in our solar system, they may shape the destinies of planets and the lives that emerge upon them. Long-period comets, the mysterious travellers that suddenly appear in our skies after wandering for countless years in the farthest reaches of space, have fascinated astronomers for centuries. These comets, with their glowing tails stretching like cosmic brushes across the night sky, seem to arrive without any clear pattern, often startling observers and challenging our understanding of the solar system. Traditionally, scientists have explained their sudden appearances by pointing to the Oort Cloud, a vast spherical shell of icy bodies imagined to surround our solar system at an almost unimaginable distance. According to this idea, the Oort Cloud is the birthplace of these long-period comets, gently nudged inward by gravitational interactions with nearby stars or the subtle tug of the Milky Way itself, only to plunge into the inner solar system where we can finally see them. But what if the Oort Cloud is not the full story, or even exist at all? This is not just an idle question. It is one of the most unsettling possibilities in modern astronomy, and yet it is precisely this kind of unsettling thought that drives science forward. Questioning assumptions, challenging models, and imagining alternatives are the ways we learn more about the universe. While the Oort Cloud offers a tidy explanation for the origin of these comets, it remains, at the end of the day, a theoretical construct. No human being has ever seen it. No spacecraft has ever ventured to its icy boundaries. No sample has ever returned from its frozen depths. It exists in equations, simulations, and scientific papers, but it has not been directly observed. This is a subtle but important distinction. The Oort Cloud is a model designed to match the data we have, not a physical structure we can point to with certainty. If we never manage to reach it, if icy fragments never find their way back to Earth, or if the paths of new comets begin to tell a story that does not fit the Oort Cloud scenario, then astronomers may eventually be forced to confront a radical possibility. Perhaps these long-period comets are coming from somewhere else entirely, from a region of space we have not yet imagined. So, if we remove the Oort Cloud from the picture, where might these comets originate? They cannot simply appear from nothing. Their elongated orbits, stretching like thin threads from the depths of the solar system into the warmth of the inner planets, suggest that they begin their journeys in regions far beyond the planets we know. Yet these distant regions are faint and nearly invisible to us, their icy denizens hidden in darkness. If not from a vast spherical cloud, then perhaps there is another kind of reservoir, a hidden storehouse of icy bodies, lying quietly in the outskirts of our cosmic neighbourhood. A deep freezer of comets, if you will, waiting for some nudge to send them inward. One of the most intriguing possibilities is that these comets come from a disc-shaped structure, flatter and more elongated than the classical Oort Cloud, perhaps even tilted at an unusual angle compared to the orbits of the planets. Unlike the imagined spherical cloud, this structure would resemble a thick warped band or ring, shaped over billions of years by gravitational interactions with planets and passing stars. It may have formed alongside the Kuiper Belt and the scattered disk, remnants of the solar system's turbulent youth, when countless icy bodies and planetesimals jostled and collided under the chaotic influence of the young sun's gravity. Over time, the movements of nearby stars or wandering rogue planets could have nudged these icy objects into the elongated paths we observe today, sending them inward as long-period comets. Yet another possibility is even more radical and challenges our very sense of cosmic boundaries. Some long-period comets may not belong to our solar system at all. This idea became more tangible after the discovery of Oumuamua in 2017 and the interstellar comet Borisov in 2019. Both of these objects arrived from the depths of interstellar space, travelling at tremendous speeds, passing through our solar system as fleeting visitors from other star systems. Could some of the long-period comets we have been watching for decades actually be similar interstellar immigrants, misidentified as members of our solar system? The mechanism for this is fascinating. As the solar system drifts through the Milky Way, it sometimes passes through clouds of wandering debris, loose icy fragments that have been expelled from other star systems. If one of these fragments happens to approach the Sun under the right conditions, its speed, trajectory and angle aligning just so, then the Sun's gravity can capture it, pulling it into an orbit that makes it a part of our solar system, at least temporarily. Once captured, it might loop around the Sun on a long, narrow path, eventually plunging inward to become a visible comet. In essence, an interstellar traveller transforms into a local celestial citizen, its identity forever changed by the gravitational pull of our star. However, there is a catch. For interstellar capture to explain the number of long-period comets we see, this process would need to happen quite frequently. At present, astronomers do not have enough evidence to say that it happens often enough to account for the observed population. Nonetheless, the very possibility reminds us that there may be multiple sources of long-period comets, and that our assumptions about the Oort Cloud may only be part of the story. Some scientists have looked closer to home for answers, considering that perhaps the outer solar system itself is more complex and chaotic than traditional models suggest. Interactions between the giant planets, Jupiter, Saturn, Uranus and Neptune, and the Kuiper belt may be far more intricate than we realise, capable of sending icy bodies into the elongated orbits that produce long-period comets. Moreover, the hypothetical Planet 9, a massive distant planet that has yet to be observed, could be responsible for flinging comets inward from regions much closer than the supposed Oort Cloud. Such gravitational interactions would be rare, but when they occur, they could send comets on dramatic inward trajectories, requiring no distant icy sphere at all to explain their existence. Some researchers even trace the origins of these comets back to the very birth of the solar system. Billions of years ago, our cosmic neighbourhood was crowded, messy and violent. The young sun was surrounded by swarms of icy planetesimals and larger bodies, colliding, merging and scattering in every direction. In this primordial chaos, some comets may have been launched into their long-period orbits, destined to wander the outer solar system for billions of years before finally making their way inward. If these orbits are stable over long-time scales, then comets may not require a distant reservoir at all. They may simply be the surviving remnants of the solar system's earliest, most chaotic dances, ancient travellers from an era we can only glimpse through careful observation and computer simulations. Of course, each of these alternative theories comes with challenges. Some cannot account for the sheer number of comets we observe, others fail to match the precise shapes and orientations of their orbits. Some require rare circumstances, highly specific alignments of planets, stars or interstellar objects. This is why the Oort Cloud remains so compelling. Despite being unconfirmed, it provides a simple, elegant framework that fits the data, predicts cometary paths, and offers a narrative for the outer reaches of the solar system. If the Oort Cloud turns out to be a mirage, our view of the solar system changes dramatically. Its edges would shrink, the boundary between the known and the unknown becoming less defined and more uncertain. Many of our current ideas about the solar system's formation and evolution hinge on the existence of the Oort Cloud. For example, the mechanisms by which Jupiter and Saturn fling objects outward, the ways in which passing stars shape distant regions, and the protection provided to inner planets from potentially catastrophic impacts. All of these ideas rely, at least in part, on the existence of a distant icy sphere. Without it, we would need to rethink and revise many of the assumptions that have guided planetary science for decades. The implications are not just scientific, they are cultural as well. The Oort Cloud is one of the rare scientific concepts that has captured the public imagination. It appears in documentaries, books, lectures, and casual discussions, often described as a shadowy boundary marking the edge of our solar system. It has become a symbol of the unknown, an emblem of the vast, frozen darkness that lies beyond the planets. If it turns out to be a placeholder rather than a physical reality, it reshapes our sense of cosmic geography. The boundary between Earth and the stars would become fuzzier, more open-ended, a reminder that the universe is not neatly divided into familiar compartments. Yet even if the Oort Cloud is never directly observed, the quest to understand the origins of long-period comets is far from over. Our questions grow sharper as instruments improve, as telescopes become more sensitive, and as new methods of observation allow us to study the faintest reaches of the solar system. The history of science is full of once solid ideas later replaced by better explanations. The ether, the steady-state universe, even the debate over Pluto's planetary status. The Oort Cloud may one day join this list, either confirmed as a real structure or relegated to the role of a useful but unproven hypothesis. For now, it remains one of the largest unanswered questions in planetary science, a concept too distant to touch, yet too useful and compelling to ignore. This ongoing mystery underscores a broader lesson about science itself. Knowledge is provisional, always subject to revision as new evidence emerges. What seems certain today may be questioned tomorrow. Long-period comets, whether they come from the imagined Oort Cloud, a hidden disk, the chaotic outer solar system, or even other star systems, remind us of the limits of human understanding and the vast, unexplored spaces that still lie beyond the reach of our instruments. Each comet that streaks across the sky is a messenger, a traveller from the hidden reaches of our cosmic neighbourhood, hinting at stories that span billions of years and trillions of kilometres. The study of these icy wanderers also highlights the interplay between observation and theory. Astronomers observe their orbits, their brightness, their chemical composition, and their behaviour as they approach the Sun. From these observations, models are constructed, hypotheses formed, and theories refined. And yet all models are provisional, built on the best data available but always subject to revision. The possibility that the Oort Cloud does not exist reminds us that even the most elegant theories must ultimately face the test of reality, the slow and deliberate scrutiny of evidence. In the meantime, the search for the origins of long-period comets continues to inspire innovation. Telescopes and space missions probe deeper and farther than ever before. Robotic spacecraft are designed to chase down these icy bodies, study their composition, and perhaps even return samples to Earth. Advanced simulations recreate the early solar system, modelling billions of years of gravitational interactions, collisions, and migrations. And as we gather more data, the boundaries of our understanding stretch outward, revealing new questions even as some old ones are answered. Ultimately, whether the Oort Cloud exists or not, the fascination with long-period comets endures. They are reminders of the vastness of space, the complexity of celestial mechanics, and the enduring mystery of origins. They challenge our assumptions, spark our curiosity, and connect us to a universe that is far larger and stranger than the one we can directly observe. Each comet is a silent ambassador from the outer solar system, or perhaps from beyond it, carrying with it clues about the history of our cosmic home, the dynamics of distant regions, and the processes that have shaped our corner of the galaxy. In the grand story of the cosmos, long-period comets are like whispered messages from the dark, icy reaches of the solar system. They hint at structures and histories that remain largely hidden, yet they are visible enough to remind us that there is always more to discover. Whether they originate from a distant spherical Oort Cloud, a hidden disk of icy bodies, chaotic interactions in the outer solar system, or the far reaches of interstellar space, they challenge our understanding and keep the spirit of inquiry alive. They tell us that the universe is never simple, that every explanation is provisional, and that the edges of knowledge are always waiting to be explored. So, the next time a bright comet suddenly appears in the night sky, stretching its luminous tail across the heavens, remember that its journey may have begun billions of kilometers away in a place we cannot yet see. It may carry within it the echoes of the solar system's violent youth, or the secrets of a star system far beyond our own. It is a traveller through time and space, a messenger from the hidden reaches of the cosmos, and a symbol of the endless curiosity that drives humanity to look up, wonder, and explore. The question of its origin, the question of where all long-period comets come from remains one of the greatest mysteries in astronomy, and whether the answer lies in the Oort Cloud, a hidden disk, interstellar space, or the chaotic outskirts of the solar system, the journey of discovery continues, as vast, mysterious and compelling as the comets themselves. Long-period comets is not just about distant ice and gravity. It is about the very process of science, the way we construct understanding from observation, theory, and imagination. It is about the courage to question long-held assumptions, to explore uncomfortable possibilities, and to recognize that the universe is far more complex and beautiful than we can yet fully comprehend. The Oort Cloud, real or imagined, stands as a symbol of that complexity, a reminder that some mysteries are too distant to touch, yet close enough to inspire wonder and inquiry. And in that sense, these comets are more than celestial objects. They are invitations, calling us to continue the exploration, to seek answers, and to embrace the unknown. Humanity's reach into the depths of space is still limited by the speed of the machines we've created. Even the fastest spacecraft we have ever launched take decades to arrive at the outer planets of our solar system. For instance, Voyager 1, launched in the year 1977, took over 12 years to reach Saturn, and more than 35 years to arrive at Neptune. These journeys, while remarkable, highlight just how vast the distances in our solar system truly are. The Oort Cloud, a hypothetical and distant region of icy objects believed to surround the Sun at the very edges of the solar system, lies far beyond even the most distant planets. To send a spacecraft there within a human lifetime would require technology so advanced that it surpasses anything humanity has ever built. Some scientists estimate that a probe capable of reaching the inner boundary of the Oort Cloud in a reasonable time frame would need to travel at speeds of at least 20 to 30 astronomical units per year. To clarify, 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers or 93 million miles. At these extraordinary speeds, a journey to the inner Oort Cloud might take roughly 70 to 100 years. That is still an incredibly long time, decades that would stretch across most human lifespans, but in the grand scale of cosmic exploration, it is not impossible. With future technological breakthroughs, the time required could be reduced even further, opening doors to a new era of deep space exploration. Over the past several decades, one concept that has captured the imagination of scientists and engineers alike is the idea of solar sails. Picture, if you will, a spacecraft equipped with enormous, ultra-thin sheets that function much like the sails of a ship, except instead of catching wind, they catch the gentle pressure of sunlight. Sunlight, though composed of massless photons, carries momentum, and when these photons strike the sail, they impart a tiny push to the spacecraft. Alone, this push is minuscule, almost imperceptible, but over months and years, as the spacecraft drifts farther from the Sun, this tiny force can gradually build up, accelerating the probe without the need for any traditional fuel. Unlike chemical rockets, which burn fuel quickly and then coast, a solar sail could steadily gain speed for decades, making it an ideal candidate for long, slow journeys into the outer reaches of the solar system. Solar sails are not merely a fanciful idea from science fiction. They have already been tested in real missions. Japan's Ikaros spacecraft, launched in the year 2014, demonstrated that a solar sail could operate successfully in space, while the Planetary Society's light sail missions proved that solar sailing could be achieved with small, relatively low-cost spacecraft. Imagine, then, what could be accomplished with a larger, more advanced sail, paired with a lightweight but robust spacecraft. The potential for continuous, decades-long acceleration could bring the Oort Cloud within reach, allowing humanity to touch a region of space that has remained untouched since the birth of the solar system. Another possible avenue toward reaching the outermost edges of our solar system is nuclear propulsion. This concept includes systems such as nuclear electric engines or nuclear thermal rockets. Unlike chemical rockets, which rely on the combustion of propellants to produce thrust, nuclear engines can provide far stronger and more enduring acceleration. In a nuclear thermal rocket, nuclear reactions heat a propellant, such as hydrogen, which is then expelled at high speed to produce thrust. In a nuclear electric engine, the heat or radiation generated by nuclear reactions is converted into electricity, which then powers ion thrusters capable of gradually but continuously accelerating a spacecraft over many years. Such systems could allow a spacecraft to continue accelerating long after it has left the protective grip of the inner solar system, slowly but steadily approaching speeds previously unimaginable for human-made machines. Nuclear propulsion, however, is not without its challenges. Technical difficulties abound, from managing the intense heat of a nuclear reactor to shielding sensitive electronics and instruments from radiation. Safety concerns are also paramount, as the potential for accidents during launch or in space must be meticulously mitigated. Yet, despite these hurdles, several space agencies are revisiting nuclear-powered flight for ambitious missions to the outer planets, and perhaps one day, to the Oort Cloud itself. Even more daring ideas exist, some of which still reside in the realm of science fiction. One such concept is fusion-powered spacecraft. Fusion, the process that powers the sun, releases tremendous amounts of energy by fusing light atomic nuclei together. A fusion engine could, in theory, produce far more thrust and energy efficiency than any chemical or nuclear thermal rocket, potentially allowing a spacecraft to reach interstellar speeds. Another extraordinary idea is beamed propulsion, in which powerful lasers or microwave beams from Earth, or perhaps the Moon, could push a tiny, ultralight probe across the solar system. The principle is simple: light carries momentum, and concentrated beams directed at a reflective sail could accelerate the probe to speeds much greater than those attainable with conventional fuel. However, these methods would require monumental breakthroughs in energy production, materials science, and autonomous navigation. The engineering and technological challenges are staggering, but the rewards, if achieved, could open the door not just to the Oort Cloud, but to the stars themselves. Speed, however, is only one of the many challenges in sending a spacecraft to the distant reaches of our solar system. Power is another crucial concern. Sunlight, the lifeblood of solar panels, fades quickly as one moves away from the sun. By the time a spacecraft reaches Pluto, sunlight is already too weak to generate significant electricity with ordinary solar panels. At the distances of the Oort Cloud, sunlight is a pale, almost ghostly glow, thousands of times weaker than what we experience on Earth. This means that any spacecraft venturing so far must carry its own independent power source. Today, we rely primarily on radioisotope thermoelectric generators, or RTGs, which convert the heat released from the decay of radioactive isotopes into electricity. The Voyager spacecraft and New Horizons, which flew past Pluto in the year 2015, used RTGs to power their instruments and communications for decades. But even RTGs have limits. Their power output decreases gradually over time, and for a mission lasting a century or more, this presents a significant challenge. A probe bound for the Oort Cloud would require either greatly improved RTGs or entirely new power systems, perhaps miniature nuclear reactors engineered to operate safely and reliably in extreme cold for many decades. Designing such a system is no small feat, but without it, the spacecraft would be blind, unable to power its instruments, sensors, or communications. Communicating across such vast distances presents yet another formidable obstacle. Even the Voyager 1 spacecraft, our farthest human-made object, now more than 48 years into its journey, takes over 22 hours for a signal to travel back to Earth. A probe positioned deep within the Oort Cloud could take weeks for a message to reach us, even at the speed of light. The signals would arrive faint and fragile, necessitating enormous antennas on Earth, equipped with extremely sensitive receivers to capture even the slightest whisper from billions of kilometers away. The spacecraft itself must carry a transmitter powerful enough to send data across the void, consuming precious energy in the process. Every watt of power must be carefully managed, and even then, communications would be slow and intermittent, a far cry from the instantaneous exchanges we take for granted on our planet. Navigation is an equally daunting task. Within the inner solar system, a spacecraft can rely on the familiar presence of planets, moons, and other celestial landmarks to guide its path. Beyond Neptune, and especially as it approaches the Oort Cloud, these reference points vanish. The Oort Cloud is a vast, sparsely populated region, filled with tiny icy objects scattered across unimaginable distances. Colliding with even a small body could destroy a spacecraft instantly. Hitting a specific object deliberately would be akin to aiming for a single grain of sand in the middle of the ocean, while both drift and currents shift unpredictably. To survive, a probe must possess systems capable of detecting and avoiding small objects autonomously, or it must receive extraordinarily precise instructions from Earth. Either option requires technology that can operate perfectly for decades, with no room for error. Every sensor, every thruster, every instrument must function flawlessly, even as components age and the harsh environment of space takes its toll. Even if these immense technical hurdles are overcome, the question of the mission's goals remains. What is the probe supposed to do once it arrives? Should it merely fly past the icy objects, taking photographs and measurements as it goes? Should it attempt to slow down and enter orbit around one of these bodies, an almost unimaginable engineering challenge so far from the Sun's gravitational pull? Or should it attempt the ultimate feat, to collect samples and bring them safely back to Earth? Each of these possibilities introduces additional layers of complexity. A flyby mission is the simplest, yet it provides only a brief glimpse into the ancient icy world. Attempting to orbit an object would require enormous amounts of energy and precise maneuvers. Retrieving samples and returning them to Earth is the pinnacle of difficulty, demanding that materials survive the rigors of long-term storage, re-entry, and the journey back across billions of kilometers. Despite these seemingly insurmountable obstacles, many scientists and engineers remain convinced that a mission to the Oort Cloud is achievable. They argue that such a mission would represent humanity's next great leap in space exploration, comparable to the first journeys to the Moon or the pioneering voyages of Voyager into the unknown reaches of the outer planets. To accomplish it, society would need to think on a scale of decades, or even centuries, longer than a single human lifespan. Spacecraft would have to be designed to endure not just years, but entire lifetimes, functioning reliably over timescales measured in generations. Achieving this would require a coordinated, sustained effort by the international community, continuous funding, and a vision that transcends the short-term horizons of politics and economics. The scientific returns might not even be fully appreciated by the generation that initiates the mission. Instead, the knowledge could be studied by scientists who are not yet born in ways we cannot yet imagine. But the potential rewards are profound. Studying the Oort Cloud directly could transform our understanding of the solar system's formation, the origins of comets, and the early history of our cosmic neighbourhood. The Oort Cloud, if it truly exists as theorized, represents the farthest and most mysterious frontier of the solar system. It is a region of silent, icy sentinels, lingering at the edges of the Sun's gravitational influence, largely untouched since the birth of the solar system over 4.5 billion years ago. A mission to this region would become the longest journey ever undertaken by humanity's machines, a journey that might span lifetimes and challenge the limits of our engineering, imagination, and perseverance. Such a voyage would be more than a scientific expedition. It would be a testament to the relentless human drive to explore, a statement that we are willing to reach into the cold darkness in search of knowledge, even when it lies at the very edge of what we know. In imagining this mission, one is compelled to reflect on what it means to explore the unknown. Humanity's history is filled with journeys into uncharted territories, from the first migrations out of Africa to the voyages across vast oceans, from the early flights into Earth's atmosphere to the first footsteps on the Moon in the year 1969. Each of these ventures required courage, ingenuity, and a willingness to endure hardship in pursuit of knowledge. The Oort Cloud represents a new kind of frontier, not one shaped by water or air, but by the emptiness of space itself, punctuated by icy relics that have drifted for billions of years, untouched and unaltered. Reaching this region will demand technologies and ideas that today reside mostly in laboratories or on the pages of speculative fiction. It will require spacecraft capable of self-sufficiency, autonomous decision-making, and long-term resilience. It will demand breakthroughs in propulsion, power generation, navigation, and communication. And above all, it will require patience, vision, and a commitment to goals that exceed the lifespan of any one individual. Among the many challenges, the human imagination continues to play a critical role. Concepts once deemed impossible, such as sending spacecraft to other planets, or even beyond the solar system, have gradually become reality. Similarly, Ideas that now seem fantastical, like fusion-powered ships or beamed laser propulsion, may one day become feasible. Each incremental advancement, from testing small solar sails to developing more efficient nuclear propulsion systems, builds the foundation for the grand voyage to the Oort Cloud. Engineers and scientists must not only solve the technical problems of propulsion, power and navigation, but also envision how such a mission can remain viable over decades of operation in a hostile and distant environment, far from any possibility of immediate repair or resupply. Another aspect of the challenge is the extreme cold and radiation environment that the probe will encounter. Beyond Neptune, temperatures drop to near absolute zero, and cosmic rays and solar radiation, although diminished in intensity, still pose risks to electronic systems and materials. The spacecraft must be insulated and shielded in ways that preserve functionality for decades, ensuring that sensors, cameras, scientific instruments, and communication systems continue to operate without degradation. Materials must be chosen not only for strength and lightness, but also for longevity under conditions that no human has ever experienced directly. Every decision, from the size of the antenna to the composition of the sail, from the type of power source to the design of thrusters, must consider the decades-long mission ahead. Consider also the profound philosophical implications. A mission to the Oort Cloud is not just a journey of machines, it is a journey of ideas, extending humanity's reach across time and space. The spacecraft becomes a messenger from one generation to the next, carrying with it not only instruments and sensors, but also the curiosity, ambition, and courage of the people who designed it. The data returned will inform science for generations, shedding light on the history of the solar system, the processes that formed comets, and perhaps even the early conditions that set the stage for life on Earth. It is a mission that transcends individual lifetimes, a project that requires thinking in centuries rather than years, demanding patience, foresight, and unwavering commitment. The practical realities of the journey are staggering. Communication delays, power constraints, navigation over billions of kilometers, and the potential hazards posed by tiny, fast-moving icy bodies. All of these require systems of extraordinary reliability and sophistication. Yet, the human story of exploration is one of overcoming the impossible. From crossing oceans to stepping onto the moon, we have repeatedly turned what was once unimaginable into reality. The Oort Cloud, distant and silent, offers another stage on which humanity can demonstrate its ingenuity and determination. It is a region where comets are born, where remnants of the early solar system lie frozen, and where the secrets of our cosmic origins may still be preserved. To reach it would be to touch the very edges of our understanding, to see what no eye has ever seen, and to bring back knowledge that could reshape our understanding of the solar system and our place within it. Finally, the vision required for such a mission demands international collaboration, long-term commitment, and a collective will that transcends politics and individual ambition. A spacecraft designed to explore the Oort Cloud will need to outlive generations of scientists and engineers, to operate autonomously across decades, and to convey information back to a planet that may itself change dramatically during the mission's lifetime. Funding, technological development, and sustained interest must all align over a century or more, a challenge not only of engineering, but of human organisation and foresight. Yet, if humanity succeeds, the reward will be unparalleled. The first close glimpse of the farthest reaches of our solar system, an understanding of the ancient icy bodies that orbit silently in the darkness, and a testament to our enduring curiosity and desire to explore. The Oort Cloud, existing or not as theories suggest, remains the ultimate frontier of our solar system. It is a place where time seems to stand still, where icy objects have drifted untouched for billions of years, and where the influence of the sun is faint but persistent. A mission there would represent the longest journey ever undertaken by human technology, a journey that could span multiple generations. It would be a tribute to human curiosity, an acknowledgement that even in the cold, dark reaches of space, we seek knowledge. It would affirm that humanity is willing to reach beyond the familiar, to embrace the challenge of the unknown, and to pursue understanding in the farthest corners of our cosmic neighbourhood. Such a journey, if accomplished, would not only expand the boundaries of science, but also elevate the human spirit, demonstrating that our desire to explore, learn, and understand is boundless, just like the universe itself. Reaching the distant, frozen realm of the Oort Cloud with the rockets we currently have is, in practical terms, nearly impossible. Imagine trying to cross the entire Atlantic Ocean in a tiny canoe with only your arms to paddle and no wind to help you. Technically, you could do it, but the effort would be staggering, the journey unbearably slow, and the chances of success minimal. In the same way, the spacecraft we have sent into space so far, even our fastest, such as Voyager and New Horizons, would require tens of thousands of years to reach the outermost edges of this icy cloud. The distances are simply mind-boggling, so vast that they almost defy human comprehension. To even consider sending a probe there within a human lifetime, we would need propulsion systems that go far beyond anything humanity has yet invented. We need a revolution in technology, not just incremental improvements on existing rockets. Yet, if we allow ourselves to think boldly, far beyond the confines of current engineering and laboratory capabilities, we can start to imagine possibilities that feel more like visions of the future than the reality of today. These are not small upgrades to the chemical rockets we know, the ones that burn fuel explosively for a brief push before drifting quietly into space. No, these are entirely new ways of thinking about how a machine might travel through the void between the stars, and if even one of these ideas could be realized, it could carry humanity, or at least our creations, deep into the Oort Cloud, perhaps even beyond it, toward other star systems and entirely new worlds. Consider the concept of a fusion engine. Unlike chemical rockets, which rely on rapidly burning fuel to produce a momentary burst of speed, a fusion engine would harness the same energy that powers the sun. At its heart, fusion is the process of taking light atoms, hydrogen for example, and forcing them together under extreme pressure to create heavier atoms like helium. This process releases enormous amounts of energy, far beyond anything chemical reactions can achieve. In other words, fusion doesn't just burn, it transforms matter into energy in a way that is unimaginably powerful, efficient, and long-lasting. If humans could one day control fusion in a steady, sustainable way, it would open doors to engines capable of continuous thrust lasting for years. Imagine a spacecraft that accelerates slowly but relentlessly, picking up speed across the vastness of space. Unlike our current rockets, which quickly exhaust their fuel and coast on the momentum gained from a short burn, a fusion-powered craft could keep going, steadily building up velocity over months, years, and even decades. On Earth, scientists have been working for decades to achieve controlled fusion, but it remains a formidable challenge. Facilities such as the Princeton Plasma Physics Laboratory in the United States, along with international collaborations like the ITER project in France, are progressing slowly, testing new designs and exploring the limits of plasma containment and energy efficiency. Now, imagine taking that technology and placing it aboard a spacecraft. Instead of a fiery roar that fades after a few minutes or hours, a fusion engine could hum quietly, steadily increasing its speed year after year. The ideas are not merely theoretical. In the 1970s, engineers and physicists envisioned a spacecraft called Daedalus, sometimes mistakenly referred to as Daedalus. This ship would use tiny pellets of fusion fuel, each detonated by precisely aimed beams of electrons. Calculations suggested that such a craft could reach speeds of roughly 1/10 the speed of light. To put that into perspective, if a chemical rocket took centuries to reach the inner Oort Cloud, a Daedalus-like fusion ship could arrive in just a handful of years. That would transform the idea of interstellar travel from an almost impossible dream into a conceivable mission. Later refinements to these concepts, such as the Icarus project, pushed the calculations even further, refining the engineering, improving fuel efficiency, and considering the challenges of materials, navigation, and safety. But the challenges are enormous. It is not only the engine that must be perfected, the ship itself must withstand decades of harsh conditions. Extreme heat, cosmic radiation, and mechanical stress would all threaten the integrity of the spacecraft. It would also have to navigate billions of miles with remarkable autonomy, making real-time decisions without waiting for instructions from Earth, because even light takes hours to travel the distances involved. Another fascinating concept merges the ideas of a solar sail and a fusion rocket. Known as a fusion sail, it works not by a narrow jet of thrust, but by spreading the force over a large area. Small fusion charges, or perhaps an onboard reactor, would produce plasma, a hot charged gas, which would be directed over a vast magnetic field like a paddle in space. The ship could then glide on this energy wave, combining smooth, steady acceleration with immense power. Such a design might reduce wear on engines while allowing unprecedented speed and distance, taking humans, or their machines, far beyond the limits of today's technology. But propulsion is not the only obstacle. Time itself becomes a significant challenge when we consider trips to the farthest reaches of the Oort Cloud. Even with incredibly powerful engines, the journey could stretch beyond what a human body can endure while awake. That is where the concept of hibernation or suspended animation comes in. Though it sounds like science fiction, it is grounded in the natural world. Many Earth animals, from bears to frogs, slow their bodily functions during winter, reducing energy use, lowering body temperature and conserving vital resources. Scientists believe humans might one day replicate this process, cooling the body to just above freezing and slowing metabolism to keep a person alive but asleep, as if pausing time. Initial experiments have already been conducted on a smaller scale. In emergency medicine, doctors sometimes cool patients to preserve brain function after severe injuries or heart attacks. The next step would be to develop techniques capable of keeping humans in this state safely for months or years. Success would mean less need for food, water, or oxygen during extended space missions, reduced physical and mental stress, and perhaps even improved repair of cellular damage caused by cosmic radiation. Yet, the dangers are significant. Any failure during hibernation could be catastrophic. Awakening could bring unforeseen health issues, and the technology would need to be foolproof before human lives could depend on it. Because of these immense challenges, many scientists expect the first expeditions to the Oort Cloud to be robotic. Machines do not need oxygen, food, water, or sleep. They can withstand extremes that would kill humans, operating for decades in environments that would be utterly inhospitable. Yet even robotic missions require leaps in technology. To be effective, probes would need artificial intelligence capable of making decisions independently, performing repairs, and steering themselves through a maze of icy objects. Waiting for commands from Earth would be impractical, as communication could take hours or even days. Artificially intelligent probes could scan the Oort Cloud, choose what to study, adjust their trajectories, and send only the most valuable information back to Earth. Rather than one enormous craft, the future might involve fleets of small, smart probes, each exploring different regions of this vast invisible cloud, and pooling their discoveries to create a complete picture of the distant frontier. And if we let imagination soar even higher, we reach the most radical concept of all, the warp drive. Unlike any engine humanity has ever conceived, this idea does not rely on speed alone. Instead, it manipulates space itself, stretching it behind a vessel and compressing it in front, effectively moving the ship without technically exceeding the speed of light. The most famous theoretical version, the Alcubierre drive, would require what physicists call exotic matter with negative mass, something that has never been observed. The energy demands are staggeringly high, potentially exceeding the combined energy of all matter in the universe. Despite these obstacles, warp drive concepts serve an important purpose. They expand our thinking, showing that even the laws of physics may contain possibilities we have yet to understand. Ideas like fusion sails, hibernation pods, AI-driven probes, and warp drives may sound like science fiction, yet so did chemical rockets a little over a century ago. In the early 1900s, the notion of reaching orbit was dismissed by most as fantasy. Yet in the 21st century, humanity routinely places satellites in orbit, sends rovers across the Martian surface, and launches telescopes far beyond the solar system. Every achievement begins with a dream that seems impossible until it becomes inevitable. The journey to the Oort Cloud will be no less challenging. It will require imagination, courage, patience, and the willingness to face risks unlike any humans have yet undertaken. But as humanity has always been drawn to the stars, so too will this distant icy cloud at the edge of our solar system continue to pull our curiosity and ambition outward. It represents the ultimate frontier, the final boundary of the sun's influence, and a gateway to understanding the birthplaces of comets, and perhaps even the early history of the solar system itself. Some of the very first human-made objects may already be on a trajectory that will eventually carry them into this remote region. When the twin Voyager spacecraft were built and launched in the 1970s, their designers were focused on much closer targets, the giant outer planets. Voyager 1 and Voyager 2 were tasked with travelling to Jupiter, Saturn, Uranus, and Neptune, capturing the first detailed images and collecting data that no human had ever seen before. They were intended to last only long enough to complete these missions and then drift silently into the vast void. Yet, almost 50 years later, these spacecraft are still operational, continuing to send whispers from the edge of our solar system. Voyager 1, in particular, made history when it crossed the heliopause, the boundary where the solar wind from the sun yields to the true interstellar medium. For the first time in history, humanity had sent a creation beyond the protective bubble of the sun, into the darkness between stars. It is a profound reminder that even humble beginnings, designed for local objectives, can eventually touch the very edges of human understanding. And yet even this achievement is small compared with the Oort Cloud. To grasp its immensity, imagine shrinking our solar system down to the size of a beach ball. All the planets, from Mercury closest to the Sun to Neptune at the outer edge of the traditional planetary realm, would fit inside a tiny pea at the centre of that ball. The Oort Cloud, however, would surround this beach ball at a distance of several meters, forming an almost invisible halo that stretches far beyond the reach of sunlight and the planets we know so well. That is the scale we're dealing with, a vast expanse of icy objects and comets stretching across billions of kilometers, silent, distant, and waiting for humanity, or our machines, to arrive. Travelling to this remote region will not be a simple journey. Every step will test the limits of human ingenuity. The engines must be revolutionary, able to push machines across enormous distances without faltering. Spacecraft must be self-sufficient, capable of navigating, repairing, and observing without direct human intervention. Crewed missions may require breakthroughs in biology, medicine, and life support systems, including the development of safe, long-term hibernation. And yet, every challenge is a testament to the human spirit, a drive to explore the unknown, to reach further than anyone has before, to take a fragment of the distant Oort Cloud and learn from it, revealing secrets that have remained hidden since the birth of the solar system. The story of humanity's push into deep space is only beginning. We have made the first small steps with Voyager, New Horizons, and other probes, but the journey to the Oort Cloud and beyond will be a saga of unprecedented ambition, requiring technology and courage that border on the fantastical, and still it beckons us. Just as our ancestors once looked across oceans, mountains, and deserts, we now look across the final frontier of the sun's influence, driven by curiosity, hope, and the irresistible call of the unknown. Someday, whether by robotic emissaries or perhaps, far in the future, by humans themselves, we will reach this mysterious, icy cloud at the edge of our solar system and uncover the stories it has silently held for billions of years. Until then, it remains a symbol of the ultimate voyage, a testament to the boundless power of imagination and the enduring pull of the stars. Imagine two small but remarkable travellers racing outward from our sun, voyaging into a realm that humanity has only begun to dream about, the farthest reaches of our solar system, a place of cold and silence so profound that it boggles the mind. These travellers are Voyager 1 and Voyager 2, spacecraft launched decades ago with a mission that at the time seemed daring and extraordinary, but now feels almost mythical. They were never meant to reach the edge of everything we know, yet here they are, silently hurtling outward, heading toward a distant, mysterious region of icy bodies known as the Oort Cloud. At the pace Voyager 1 currently moves, reaching the inner edge of this vast cosmic cloud would take more than 300 years. To put that into perspective, 300 years is longer than the span of the United States' history as a nation. It is nearly 2 full generations of human civilization. Voyager 2. Moving along a slightly slower path and set on a subtly different trajectory will take even longer. Its journey will stretch across centuries as well, and yet, despite the enormous distances and the immensity of space, both Voyagers continue their slow, steady march outward, unassisted and untethered, propelled by the momentum gifted to them at launch decades ago. Nothing can steer them now, and nothing can stop them, short of the random chance of a collision with some rogue object. But what awaits these Voyagers in the distant reaches of the Oort Cloud? The answer, perhaps surprisingly, is that almost nothing will happen. The Oort Cloud is so enormous that even though it may contain billions, or perhaps even trillions of icy worlds, these objects are scattered so sparsely across unimaginable distances that a spacecraft could pass through without ever touching one. Voyager 1 and 2 have no engines left to burn, no fuel to maneuver, and no means of stopping. They will drift onward, silent and eternal, their metal frames carrying the echoes of human ambition far into the darkness. These Voyagers are not alone in their silent pilgrimage. Earlier explorers such as Pioneer 10 and Pioneer 11 also left the sun's warmth and ventured into the unknown. Their voices faded into the void many years ago, leaving only faint traces in the deep background of space, yet their metallic hulls still glide outward, unheeded but undeterred. Later, New Horizons joined this small flotilla of wanderers, giving humanity breathtaking glimpses of Pluto in the year 2015, before it too began its lonely outward journey. In time, it too may reach the edges of the Oort Cloud, continuing humanity's reach into the outermost boundary of our solar system. Yet here lies the central challenge: time itself. The Oort Cloud is not a destination that can be reached within a human lifetime using any technology we have developed. To cross it, even in part, would take thousands of years, perhaps tens of thousands. Our spacecraft were never designed to endure such spans. Their power sources, radioisotope thermoelectric generators, weaken with each passing year. Within the coming decade, these explorers may all fall silent, their instruments cold and lifeless, their journeys continuing as empty shells drifting through the void. And yet, their importance does not vanish with silence. Even after they cease to transmit data, they remain symbols of human ingenuity. They are proof that we can build machines capable of outlasting nations, empires, and perhaps even civilizations themselves. They inspire us to imagine a future in which spacecraft might not only reach the Oort Cloud, but also endure long enough to study it in detail, to relay discoveries back to Earth from the depths of space. Such a spacecraft would require energy systems far stronger and longer lasting than any we currently possess, shielding against the bitter cold and radiation of deep space, and instruments capable of surviving the endless darkness. Today, our dreams are still tethered to the Voyagers, machines built with technology from the 1970s. By contemporary standards, these spacecraft are astonishingly primitive. Their memory capacity is tiny, almost laughable. Their processors operate more slowly than the most basic pocket calculators. Yet, despite these limitations, they continue their outward journey, carrying humanity's hopes further than any human has ever gone. In all likelihood, Voyager 1 and 2 may become the first human-made objects to enter the Oort Cloud, a region that humans themselves may never physically reach. And if, someday, humanity designs a mission specifically for this distant frontier, it will owe much to these early spacecraft. They demonstrated how immense the challenge is, how slow and arduous the journey, and how vast the emptiness beyond the familiar planets. Step by step, artifact by artifact, we are reaching outward. Yet one question lingers, almost impossibly distant. Will a human ever gaze upon the Oort Cloud within the span of a single lifetime? Let us imagine, for the sake of possibility, that we attempt such a feat. Suppose we aim to send a spacecraft to the Oort Cloud and have it arrive within 50 years. To some, 50 years may seem like a long time, a full half-century. But consider it another way. 50 years approximates the length of an ordinary working lifetime. A young astronaut beginning training at the age of 20 could feasibly witness the mission's arrival at 70 years of age. The journey would demand patience and resilience, yet it remains just within the realm of human possibility. The technological demands, however, are staggering. Such a spacecraft would need to travel at speeds roughly 10 times faster than anything we have ever launched. It would have to race outward at more than 150 kilometers every second, maintaining that astonishing velocity not for hours, days, or months, but for decades. While this does not violate the laws of physics, It stretches the limits of our current engineering. Concepts such as nuclear fusion propulsion or even antimatter engines have been proposed as future technologies capable of such feats. Yet even if we solve the problem of speed, the spacecraft would face the profound challenge of survival. Space is a hostile environment for life, and by extension, for the delicate instruments we might send to study it. Every resource, air, water, food, and power, must be carried along or produced on board. Beyond the protective bubble of Earth's magnetic field, cosmic rays and solar storms bombard spacecraft with relentless energy, damaging electronics and threatening human health. For crewed missions, the psychological challenge is immense. Months can stretch into years, and years into decades, spent in isolation with no planetary body nearby to visit, no familiar landscapes to break the monotony. The silence of the void is not merely the absence of sound. It is an oppressive, endless stillness, a depth of solitude that is almost unbearable. By comparison, even missions to Mars would appear as short, cheerful excursions. Communication over such distances presents another profound problem. While messages between Mars and Earth take only minutes, those sent from the Oort Cloud could take days, even weeks to arrive. Conversations would no longer be conversations. They would resemble letters sent across the oceans in the age of sail, slow and cumbersome. Emergencies would demand immediate autonomous action from the crew. There would be no time to wait for instructions from Earth. Every problem, every critical decision would rest solely on those aboard the vessel. Perhaps the most difficult reality is that any journey to the Oort Cloud would likely be one way. Returning to Earth after decades in transit would require enormous supplies of fuel and provisions, and introduce engineering complexities that are almost impossible to overcome. Accepting a one-way trip raises profound ethical and emotional questions. Who could bear the thought of leaving Earth forever, severing all contact with oceans, forests, cities, and the hum of human life? To survive the mission is one matter. To live with the permanence of exile is another entirely. Some scientists and futurists have imagined solutions to these challenges through the manipulation of life itself. If humans could enter a deep hibernation or suspended animation, they might sleep through most of the voyage, alleviating the need for food, water, and the passage of time. Modern medicine has succeeded in slowing life in certain animals and briefly preserving human tissue, but extending such techniques for decades in deep space remains speculative and fraught with danger. Even with advances in stasis, the crew would remain vulnerable to radiation, equipment failures, and the unpredictable hazards of interstellar travel. And what would they find upon arrival? The Oort Cloud is not a single world or planet waiting to be mapped. It is a dispersed wilderness of icy fragments and dormant cometary bodies, separated by distances so vast that a spacecraft could travel for years before encountering an object worth examining. Precision navigation would be crucial, and yet even with the best guidance, sheer luck may dictate the mission's success. In a sense, the journey itself could prove as meaningful as the destination. To reach such a remote frontier, to even pass through it, would be an act of exploration unparalleled in human history. History reminds us, however, that humanity thrives on the impossible. Our ancestors crossed oceans when charts were blank, venturing into waters rumoured to harbour monsters. They floated in balloons before anyone fully understood flight. They walked on the moon guided by computers weaker than a simple wristwatch. Exploration is inscribed in the human spirit, an unquenchable drive to extend knowledge beyond what is familiar. Perhaps in a future not bound by current lifespans or limitations, humans will live longer, aided by medicine or genetic enhancement. Perhaps new generations will be born in space, growing entirely among the stars, never setting foot on a planet. In such a future, the Oort Cloud may not mark an endpoint, but rather a first step into a vaster cosmos. For the present, though, the dream remains distant. A human born today would not live long enough to train, launch, and arrive at the Oort Cloud using our current technology. Our robotic explorers are only beginning to step beyond the planetary neighbourhood. The Oort Cloud, vast and frozen, lies far beyond, like the deepest edge of a forest yet unexplored, beyond the first trees we are only now beginning to enter. It stands as a question. Will it become an impassable boundary, a final frontier that remains forever out of reach? Or will it eventually serve as another milestone, a waypoint on humanity's endless journey of discovery. Even now, the Voyagers remind us of what is possible. They show that machines can endure far longer than their creators, drifting across time and space, carrying a fragment of human curiosity into the darkness. They teach us that journeys measured in centuries can still begin with a single launch. Step by step, piece by piece, humanity extends its reach into the void, exploring what lies beyond, imagining what may yet be. And though the Oort Cloud may not yet welcome human visitors, it waits as a silent testament to the vastness of the solar system and the enduring ambition of those who dare to venture into the unknown. Every light year beyond Earth represents both distance and discovery. Every frozen fragment of ice, every lonely comet, every whisper of cosmic dust in the outer solar system carries with it the story of a star's birth, of planets forming, of gravity shaping the unending ballet of matter. The Voyagers, drifting outward, are our witnesses and emissaries in this story, reminding us that exploration is not just about speed or survival. It is about understanding, curiosity, and the courage to gaze into the infinite and say, "We will go there." In the vastness of space, there is no fence to mark boundaries, no signpost to tell us where one region ends and another begins, and certainly no glowing line stretched across the stars with a message reading, "Stop here." Space is vast, open and boundless, stretching endlessly in every direction. Yet, as humans, we often find what seem to be edges. These edges are not made of stone or metal, nor are they cosmic walls constructed by some universal architect. Instead, they appear in the form of challenges so immense, so daunting, that they feel like invisible barriers. They are edges carved by time, distance, and the enormous effort it takes to cross them. They are places where the ordinary becomes extraordinary, and the impossible seems just within reach, yet always just out of grasp. One of these edges, perhaps the farthest edge we will ever try to reach, lies in a place called the Oort Cloud. The Oort Cloud is not a planet, nor is it a ringed giant, nor a moon waiting to be stepped upon. It is a colossal, almost ghostly shell of icy rocks, dust, and frozen remnants that orbit the sun at distances so vast that they stretch nearly halfway to the nearest stars. This shell forms an invisible bubble around our solar system, a thin veil of material lingering in the outermost reaches, untouched by the warmth of the sun, drifting in silence. From afar, if one could rise high enough above the solar system and peer downward, one would see the familiar planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all encircled by this enormous, almost imperceptible halo. The sun, bright and dominating near the centre, would appear almost lost within this sphere, as if it were a small lamp inside a cathedral of ice and stone. The Oort Cloud is more than just a distant region. It may one day serve as the outermost edge of human reach, a boundary not of iron or force, but of effort and endurance. It is not a wall, but a threshold, a frontier. Beyond it lies the realm of interstellar space, a dark, empty ocean between the stars where even the strongest radio signals would fade into silence, and where spacecraft might drift forever without returning. In this sense, the Oort Cloud is both a destination and a warning, a place where ambition meets its natural limit and where patience, ingenuity and courage are tested against the cold, vast wilderness of the cosmos. Even reaching the closest planets is no small feat. Consider Mars, our neighbouring red world. A trip to Mars demands years of planning, precise calculations, engineering so refined that a single mistake can cost billions of dollars and lives, and an endurance of time and patience almost beyond human imagination. And Mars, for all its difficulty, is still relatively near. Jupiter, Saturn, Uranus and Neptune lie even farther. Each step outward from the Sun multiplies the challenge. The distances grow, the travel times lengthen, and the demands on spacecraft technology increase exponentially. Reaching the Oort Cloud is not a matter of months, nor even a matter of a few decades. It is a journey that could last generations. In theory, machines can survive such voyages, drifting quietly through the darkness, taking snapshots of icy bodies, collecting grains of cosmic dust, sending streams of data back toward the tiny dot of Earth. For humans, however, the challenge is not only technological, it is philosophical. What does it mean for a single life to give itself to a mission that may only bear fruit hundreds of years from now, long after the explorer has passed? To pursue the Oort Cloud with human bodies alone would require courage, foresight, and patience that may be beyond any one generation's capacity. And yet, humanity has always reached for the seemingly unreachable. Perhaps one day, we will send robotic explorers into the Oort Cloud, vessels strong enough to endure the cold and dark, able to drift among the countless icy bodies that inhabit this distant region. These probes might photograph them, analyze their composition, send back maps of their scattered orbits, or even collect tiny particles left over from the birth of the solar system. Such missions would push our technology and imagination to their limits. And still, even as we touch the outermost edge, the Oort Cloud may remain a symbolic frontier. Not because it is the most difficult thing we have ever attempted, but because the effort, energy, and cost required to go beyond it may grow faster than the rewards we can hope to achieve. Each expedition will have to compete for funding, for attention, and for justification. And the further away the destination, the harder it becomes to justify the journey in the terms of immediate human benefit. Beyond the Oort Cloud stretches the vast, dark ocean of interstellar space. It is not truly empty. It contains dust, stray atoms, and scattered remnants of ancient stars. Yet the matter is so thinly spread that it is nearly negligible. Here, the universe feels like a wilderness, a place almost untouched by human presence. Crossing into this region is not simply leaving the solar system, it is stepping into the galaxy itself, a sea of stars and voids stretching far beyond the warm glow of our sun. Spacecraft venturing here would leave behind the familiar gravitational tugs of our planets, the predictable rhythms of orbits, and all the relative safety of the solar system. Here, the unknown dominates. Even light from the nearest star would feel faint, and the silence would be absolute. Human space exploration has always advanced in steps. First, there was the Moon, humanity's first foothold beyond Earth. Then came the dream of Mars, which has captured our imagination for decades, a world to explore and perhaps inhabit. In the future, we may visit the moons of Jupiter and Saturn, or even the outer planets themselves. Each of these goals builds upon what came before, forming a ladder of experience and understanding. But the Oort Cloud is unlike any of these. It is not a single world to set foot on. It is not a planet to orbit, nor a moon to land upon. It is a vast, diffuse cloud, scattered and invisible, without clear edges or landmarks. It cannot be observed easily, cannot be mapped precisely, and cannot be chased like a comet or asteroid. In a sense, it is more idea than object, a representation of the farthest reaches of our solar system, the ultimate horizon. Still, certainty has never been a requirement for human exploration. The unknown has always beckoned, and often it is enough to know that a mystery lies ahead. The Oort Cloud is more than just a place. It is a symbol of curiosity and courage. It marks the farthest edge of the solar system, where the sun's influence wanes and the galaxy begins. To reach it would be to touch fragments that were born with the planets, remnants cast into the cold darkness for billions upon billions of years. These tiny icy rocks and dust grains are storytellers of cosmic history, witnesses to the birth and evolution of our solar system, silent travellers from a time before life existed on Earth. To encounter them would be to hold in our hands a piece of deep time itself. Yet the Oort Cloud may also be the place where humanity pauses. Perhaps not forever, but for many generations it may remain the ultimate milestone. The energy, resources and ingenuity needed to go further may outweigh the benefits, at least under the constraints of current technology and thinking. Even if robotic explorers continue beyond it, human presence might never follow. The Oort Cloud could remain the last milestone, the final outpost before the vast emptiness of interstellar space stretches infinitely beyond our reach. And there is a strange beauty in this notion. There is something poetic in imagining a future where humanity stands at the edge, gazing outward into the black ocean of space, leaving behind a signal, a mark, or even just the faint knowledge that we were there, not as conquerors, but as explorers. Even without stepping foot into it, the Oort Cloud gives humanity something invaluable, an aim, a challenge, a reason to look outward and dream. Every explorer needs a distant horizon to chase, a place so far that it can only be reached with determination, patience, and imagination. Perhaps that is the true gift of the Oort Cloud. It offers a goal beyond immediate grasp, a frontier beyond the ordinary reach of human life. Perhaps that is why it exists, at least in the human story of exploration, not as an obstacle, but as a distant invitation. And there is humility in this vision. Space does not conform to human desires. The universe does not set boundaries for us. We create them ourselves. The Oort Cloud may appear as the farthest edge we can reach today, the ultimate marker of human ambition. But that may only be because our thinking, our technology, and our imagination have not yet evolved enough to reach beyond it. If humans change the way we build, the way we travel, even the way we live, the Oort Cloud may become just another stepping stone on the journey outward. If not, it may linger there for countless generations, a silent, icy sentinel marking the edge of what we dared to explore. It reminds us of our limits, even as it inspires us to push them further. Reaching the Oort Cloud is not simply a matter of distance. It is about endurance, ingenuity, and vision. It requires us to measure our patience in decades or even centuries. It requires spacecraft that can survive the cold, the darkness, and the absolute solitude of this distant realm. It demands engineers and scientists willing to dedicate their lives to a mission whose success may be measured long after they are gone. It asks us to consider the value of exploration itself, not as a practical venture with immediate returns, but as a pursuit of knowledge and wonder, of human curiosity reaching outward into the cosmos. And yet, there is a unique beauty in the impossibility. The Oort Cloud challenges us because it is so far, so silent, and so intangible. It cannot be seen with the naked eye, nor with even the most powerful ground-based telescopes in much detail. It is a ghostly collection of frozen relics, drifting in near-perfect darkness. Its sheer scale is staggering, stretching perhaps halfway to the nearest star, containing billions, perhaps trillions of icy bodies. Each one carries the memory of the early solar system, remnants of the primordial disk of gas and dust from which planets and moons emerged. To reach these fragments is to reach across time itself, to touch the beginnings of our cosmic neighbourhood. Consider the scale for a moment. Voyager 1, humanity's fastest spacecraft, launched in 1977, is still travelling at nearly 60,000 kilometres per hour. At that speed, it would take more than 300 years just to reach the inner edge of the Oort Cloud. To travel completely through it could take not hundreds, but thousands, perhaps even tens of thousands of years. Voyager 2, moving slightly slower and on a slightly different trajectory, would require even more time. And these are our fastest emissaries, machines built decades ago with technology that now feels almost quaint. Even they move so slowly in comparison to the vast distances involved that their journey to the Oort Cloud is beyond the scope of a single human lifetime. And yet, these machines persist, drifting ever onward, tiny beacons of human ambition in a sea of black. The Oort Cloud teaches us about perspective. It reminds us that human scales of time, energy, and ambition are minuscule in the context of the universe. To cross the Oort Cloud is not simply a technical challenge, it is a meditation on patience, perseverance, and the limits of understanding. It asks us to imagine civilizations not only building spacecraft to survive decades in isolation, but also passing knowledge across generations, so that missions begun today might be completed centuries hence. It asks us to think in lifetimes, not years, in millennia, not decades. In this sense, the Oort Cloud is not just an edge, it is a mirror, reflecting both our ambition and our humility. And yet, humans have never been content with boundaries. The drive to explore has carried us from Africa to the farthest islands of the Pacific, from the valleys of the Nile to the peaks of the Himalayas, from Earth's surface into orbit, and from orbit to the moon. Each frontier has seemed impossible until we reached it. Each edge, once crossed, became the foundation for the next. The Oort Cloud may be the ultimate challenge, the final horizon within the solar system, but perhaps it's only a beginning in a larger story, one that spans galaxies and eons, one that stretches far beyond what we can yet imagine. Even if humanity never reaches it in person, the Oort Cloud remains an inspiration. It challenges us to build faster, to think bigger, to endure longer. It offers a distant target for our most ambitious dreams, a reminder that exploration is not about immediate reward, but about striving toward the unknown. It embodies the tension between possibility and patience, ambition and humility. In its icy silence, it holds stories of the earliest moments of our solar system, fragments of comets and asteroids that have witnessed the rise of Earth, the birth of life, and the evolution of humanity itself. To reach it is to touch history on the grandest scale, to grasp time itself in frozen fragments drifting in the void. Ultimately, the Oort Cloud is a symbol of human curiosity and determination. It is a reminder that exploration is never easy, that the edge of what we know is always defined not by nature, but by the limits of our courage, imagination, and endurance. It is a challenge, a dream, and a horizon all at once, a place where effort meets mystery, and where every small discovery illuminates the vast darkness around it. It teaches patience, inspires ambition, and cultivates humility. And perhaps, above all, it reminds us that in the endless expanse of space, the most important boundaries are the ones we set for ourselves, and the most important journeys are those we dare to begin. Some scientists and thinkers have suggested a bold idea called simulation theory. This idea says that everything around us, from the tiniest atoms to the largest galaxies, might not be real in the way we usually think. Instead, it could all be part of a huge digital program, running on a system far beyond what we can imagine or understand. Within this strange possibility, the Oort Cloud has taken on a special kind of mystery. To many, it feels like a limit, a soft but unbroken wall wrapped around our solar system. Humanity has never crossed it, never sent a machine beyond its invisible border. Maybe it is simply the way our solar system was formed. But perhaps, just perhaps, it could also be the point where the program stops. In video games, there is something known as a skybox. This is the painted shell that makes players think they are looking at stars, faraway mountains, or endless horizons. Yet it is not real depth, just an illusion. The player can never pass through it because it is there only to show, this is the edge of your world. Some people wonder whether the Oort Cloud might be our skybox, a boundary in the big simulation, drawn only as much as it needs to be. This might sound strange, but it does not come out of nowhere. The Oort Cloud itself behaves in curious ways. First, it is extremely far from us, much farther than any spacecraft has ever gone. Second, it is so dim, scattered, and faint that even our best telescopes cannot see it directly. Third, we only know it exists because of indirect evidence, like the long-period comets that appear from its direction. That balance, between evidence strong enough to believe but faint enough to remain hidden, matches the way a clever simulation might save its resources. It looks real, but only just enough. In computer games, distant mountains are often not fully drawn until the player comes closer. This saves memory and power. Some suggest the universe might work the same way if it were a simulation. Places no one can reach stay blurry, only partly filled in. The Oort Cloud could be one of these fuzzy zones, given just enough realism to fool the observer, but not so much that the system wastes energy simulating every detail. Then there are the comets. The long-period comets that fall toward the inner solar system arrive from seemingly random directions, as though they are falling in from all sides of a huge sphere. This matches what we expect from an Oort Cloud. But in a simulation, randomness itself could be a built-in feature. It would make the system look more natural, more surprising. A comet arriving suddenly from the dark might be like a scripted event in a game, something to stir the story, to test the system, or even to reset part of it. The orbits of Oort Cloud objects are so enormous that one orbit takes far longer than the entire span of human history. No person and no civilization could ever witness a full cycle. In a simulation, this would be a perfect trick. You create the appearance of complexity, but you never actually have to finish the calculation. The process looks alive, but it never has to be completed. Consider the Voyager spacecraft. Launched in the 1970s, they have been travelling outward for nearly 50 years, yet their power will run out long before they ever reach the Oort Cloud. It is almost as if the explorers are allowed to come close, but never close enough to touch the truth. The illusion stays safe, the backstage hidden. The Oort Cloud is not only distant, it is also silent. It does not shine. It does not gather into planets or moons. It does not send signals or show motion we can follow. It just lingers at the edge, quiet and unreachable, half real and half unknown. For those who believe in simulation theory, this is exactly the sort of pattern one should expect. The cloud might not be just a collection of icy rocks. It could be part of the architecture of the simulation itself, the dividing line where the inside world stops, and beyond which no full physics is running. Like the fog walls in video games that block the player from straying too far, the Oort Cloud could be whispering, "You cannot go beyond this point." This idea unsettles us because humans dislike empty maps. We are explorers by nature. When we see a gap or a mystery, we want to fill it with meaning. Perhaps that is why the Oort Cloud has such a grip on our imagination. It is not just the edge of our solar system, it may be the edge of our belief. If the Oort Cloud truly were part of a simulation, what would that mean? Would we stop exploring, thinking the boundary cannot be crossed? Or would it make us even more determined to test it, sending probes not just to collect ice samples, but to see if the universe itself might glitch at the edge? Could the cloud be the place where we test reality itself for cracks, seams, or flickers of something artificial? For now, this remains speculation. The Oort Cloud might indeed be nothing more than what most astronomers believe it is: the slow, frozen leftovers of the solar system's early days, drifting in cold silence. Yet even so, it has become more than a scientific puzzle. It has become a stage where science, imagination and wonder all blur together. Until we go there, until our eyes see it directly, the question remains open. What is the Oort Cloud really? And what does it mean? Could it be a mere field of drifting ice? Or could it be the greatest boundary of all, the place where our universe itself shows whether it is real or simulated? At first glance, the idea feels almost impossible to believe. How could anyone ever prove that the entire universe, from the smallest atom to the largest galaxy, is nothing more than a simulation? Where would such an investigation even begin? Many people imagine it would require some grand and dramatic discovery, like finding a glowing control panel drifting through space, or spotting a line of hidden computer code shining in the night sky. But if the universe truly is being simulated, like a huge digital world created on a system beyond anything we can imagine, then maybe the edges of that world would carry clues. And one of the most mysterious edges we know of is the Oort Cloud, a giant sphere of icy bodies surrounding our solar system like a distant shell. Simulation theory itself comes from a surprisingly simple thought. If it is possible to build a simulated world filled with conscious, thinking beings, then maybe it has already been done. In fact, maybe it has been done many times before. If we ourselves live inside one of these simulations, then subtle hints might exist, strange patterns, invisible boundaries, or quiet limits hidden by whoever designed it. The real challenge is spotting those hints. One possible clue involves the idea of resolution. Think of a video game. When a player moves too far from the main area, the details in the background sometimes become blurry or less detailed. The system does not waste power creating full detail where no one is expected to go. Could our universe work in a similar way? At the outer edge of the solar system, in the deep and distant Oort Cloud, the resolution of reality itself might break down. If astronomers carefully studied how light from distant stars shines through that region, they might notice strange distortions. Perhaps the dust and ice there do not follow the usual rules of physics. Maybe instead, there is a minimum level of detail, like the pixels in a three-dimensional game world. Another idea is to test the nature of randomness. In our current understanding, quantum physics creates true randomness, though still within certain limits. But in a simulation, randomness might not be real. It could be generated by a program, numbers that only seem random, but actually repeat in subtle ways. Some scientists believe that with enough data, we could tell the difference. For example, if the arrival times or flight paths of long-period comets showed repeating patterns instead of pure chaos, that might mean a hidden artificial order exists behind the scenes. There is also the mystery of gravity. Decades ago, spacecraft like Pioneer 10 and Pioneer 11 showed small but puzzling differences in their paths, called the Pioneer anomalies. These were later explained by heat given off by the spacecraft themselves, but the event reminded us that testing the laws of gravity in deep space can sometimes lead to surprises. Imagine if a future mission to the Oort Cloud found tiny, steady shifts in gravity, changes that did not match the rules described by either Isaac Newton or Albert Einstein. That might point to a hidden structure beneath reality itself, a cosmic grid, a background clock, or artificial rules set by the system's creator. The simulation might also save resources in clever ways. Suppose we sent a probe deep into the Oort Cloud and it suddenly disappeared, not from damage, but as if it had entered an information void. What if our instruments could not properly track certain objects in that region? Or if the data changed depending on whether anyone was actively watching? That would be very strange. In a simulated world, attention itself could be part of the program. Things might only fully exist when someone is looking at them. This links to the famous observer effect in quantum physics. In real experiments, simply measuring a particle can change its behavior. Scientists accept this as a basic part of nature. But if we are inside a simulation, maybe this effect is not just natural, it could be a programmed shortcut, a way of saving processing power. Perhaps nothing at the solar system's edge becomes fully real until we send sensors there. A good test would be to compare results from passive instruments, which only watch or listen, with active ones, which send signals and interact. If the data changes greatly depending on the method, that might suggest the universe renders reality only when it is observed. Some thinkers have suggested a daring idea. What if we look for glitches in the universe itself? In video games, when players push the system too far, strange things happen. Characters might fall through the floor, distances can stretch or shrink unexpectedly, or time might behave in odd, unpredictable ways. Now imagine that one day we launch a spacecraft at incredibly high speed toward the Oort Cloud, the distant, frozen region at the edge of our solar system. If that spacecraft started sending back reports of bizarre physics, like time flowing at different rates, signals repeating over and over, or impossible shapes and geometries, this could hint that the universe is straining against its own limits. In a natural, real universe, such strange events would be almost impossible to fake, but in a simulated or programmed universe, they might be perfectly normal. Other scientists have imagined even bolder experiments, testing the very constants of physics. Things like the speed of light, the charge of an electron, or Planck's constant are believed to be the same everywhere in the cosmos. But in a simulation, these values might be adjustable. What if, for example, measurements taken in the outer solar system showed that one of these constants was slightly different from the same measurement here on Earth? Perhaps a radiation test in that distant region gave results that did not make sense. Such a discovery would be deeply unsettling. It could suggest that the universe is not uniform, not as consistent as we think, but instead follows hidden settings like a program running in the background. Some scientists go even further in their imagination. They think that if our universe is a simulation, its creators might have left subtle messages behind, much like an artist signing a painting in the corner. These messages could be hidden in the patterns of cosmic background radiation, buried within mathematical constants, or even embedded in the paths of comets drifting through space. The Oort Cloud might be the perfect place for such signatures, not because the messages would be obvious, but because this remote region is so far away and so rarely observed that the system might not bother to cover them completely. At present, humans cannot reach the Oort Cloud. It lies far beyond what any of our spacecraft can travel, remaining only a dream. Yet it still captures our imagination as a potential testing ground for the nature of reality. If we ever hope to learn whether the universe is real in the way we perceive it, or whether it is something closer to an astonishingly detailed simulation, the far edge of our solar system could be the best place to start. So, if the universe is a simulation, what might the Oort Cloud's role be in its grand design? In computer systems, boundaries are everywhere. They act like invisible fences, keeping everything organized. Boundaries divide data into sections, so one task does not interfere with another. Firewalls, memory partitions, and buffers all serve the same purpose. Without them, a system would quickly descend into chaos. Now, imagine for a moment that the universe itself is like a massive computer program. If that were true, then perhaps the universe needs boundaries too. Zones that separate what is active from what is dormant. Areas that divide what we can interact with from what we cannot. In this sense, the mysterious Oort Cloud might not just be a distant collection of icy rocks. It could be one of these cosmic boundaries. Think of it as a buffer zone. Close to the Sun, the simulation might need to run in high detail. Planets must be shown with oceans and mountains, weather systems must shift across their skies, and living beings and machines must function with all the complexity of real life. Rendering this much detail requires enormous energy. But far out in the empty, cold regions of space, where little happens, the system could conserve power. It might render objects in lower detail, fading them into a kind of cosmic fog, much like the blurry edges of a digital map in a video game. Viewed this way, the Oort Cloud could be the very place where the sharply detailed simulation of the inner solar system gradually fades into the quieter background processes of the wider universe. And what about the comets that emerge from the Oort Cloud? Maybe they are not simply wandering ice chunks. Perhaps they are test probes, not launched by us, but by the system itself. They might exist to introduce randomness into the simulation, to test that the rules still work, or to occasionally stir the inner solar system. In this sense, what we call long-period comets could be part of a vast algorithm, carefully designed to maintain balance, much like a program running background checks at regular intervals. Another possibility is that the Oort Cloud acts as a firewall. In a computer, a firewall prevents one part of the system from accessing another, blocking unwanted entry and keeping information separated. The Oort Cloud might serve the same purpose. If there is something beyond our solar system that we're not meant to see or reach, this cold, distant shell could be the barrier that protects it. And unlike a real firewall, it would not need walls, metal or fire. In a simulation, a barrier could be as simple as distance, darkness, and cold. If we cannot travel there or observe it clearly, then the barrier is working perfectly. It keeps us contained. This idea suggests something startling. There may be far more beyond our solar system than we're allowed to know. Or perhaps the Oort Cloud is like a digital fence, keeping us safely inside our cosmic playground. And it does not have to be perfect. It only needs to be distant enough, difficult enough to reach, that humanity will eventually give up trying. Some thinkers even imagine the Oort Cloud as a type of data boundary. In computer programs, not everything is loaded at once. Only what is needed at the moment is active. The rest is stored, ready to appear when someone moves closer. Just like in a video game, distant scenery might not fully exist until a player approaches it. The Oort Cloud could mark the farthest edge where the solar system's detailed simulation exists. Beyond that, space might not be fully formed at all. It could be placeholder data, waiting for a reason to become complete. This might explain why we have never directly observed the Oort Cloud. Perhaps it remains a blurry, unfinished zone, waiting for us to come close enough to activate it. This raises a fascinating possibility. What if the Oort Cloud responds to us? In some digital systems, the environment updates only when the user interacts with it. If no one looks, details remain hidden. If attention is given, the program fills in the missing information. The Oort Cloud might behave the same way. Send a probe toward it, and suddenly the system might render more detail. Ignore it, and it could remain a hazy, half-real space. And unless we witness this process in action, we might never know. The true test might not come in 10 years, or even 100 years, but perhaps in 1,000 years, when humanity finally reaches far enough to see what is really there. If the Oort Cloud is part of a greater cosmic code, its purpose might not be to hide secrets, but to shape the story of the solar system. Perhaps it slows incoming threats, making sure they do not strike too quickly. Perhaps it regulates timing, ensuring events unfold at a steady pace. Perhaps it acts as a storage zone, keeping leftover debris away from the main areas where planets and life exist. Whatever the truth may be, the Oort Cloud might not be random at all. It might not be a leftover remnant of the solar system. In this view, it could be one of the most important features of our cosmic neighbourhood, a quiet guardian, a hidden firewall, or a boundary written into the very code of reality. These are challenging questions, but when we stand at the edge of what we know, staring into the dark regions where the Oort Cloud is believed to lie, they feel worth asking. In the year 2017, astronomers all over the world were stunned by something extraordinary. A strange object had suddenly appeared in our skies, rushing through our solar system at an incredible speed. It was unlike anything we had ever seen before. This mysterious visitor entered from deep space, passed by our sun, and then, just as quickly as it came, vanished again. never to return. This traveller was given a very special name, Oumuamua. The word comes from the Hawaiian language, meaning a messenger from afar arriving first. The name was chosen with great care, for the object truly seemed like a messenger, bringing with it secrets from distant stars. Just 2 years later, in the year 2019, another visitor arrived. This one was first spotted not by a professional team of scientists, but by an amateur astronomer from Crimea named Gennady Borisov. Because he was the first to find it, the object was named Borisov in his honour. Unlike Oumuamua, Borisov was less mysterious in its appearance. It looked more like the comets we already knew, complete with a glowing tail stretching behind it. But it too had come from beyond our solar system. These two objects, Oumuamua and Borisov, had something very important in common. They did not belong to the Oort Cloud, that faraway icy shell that surrounds our solar system, like a faint sphere of frozen debris. They were not pieces of the Kuiper Belt either, the region beyond Neptune filled with icy worlds and dwarf planets, and they were not tied to the Sun by its gravity the way planets, asteroids and comets normally are. Their paths and their great speeds made it clear they were interstellar. They had travelled through the vast darkness between stars before arriving here. For astronomers, this was like finding messages sealed in bottles, drifting across a cosmic ocean and washing up unexpectedly at our shores. These objects offered a priceless chance to study the building blocks of other star systems, worlds far beyond our reach. Before Oumuamua, no scientist had ever seen an interstellar object pass through our solar system. For centuries, astronomers had imagined what might exist beyond the Oort Cloud, but these ideas were mostly speculation. Theoretical models had suggested that pieces of rock and ice might get kicked out of their home systems and drift between the stars. But most experts believe such wanderers would be unimaginably rare, perhaps so rare that none would ever be spotted in our lifetimes. Then, almost without warning, two appeared within the short span of just 2 years. This sudden discovery forced scientists to rethink their assumptions. Perhaps the space beyond the Oort Cloud was not an empty void after all. Perhaps the galaxy was alive with hidden travellers, silent wanderers drifting endlessly, waiting for chance encounters with curious worlds like ours. Let us look more closely at Oumuamua, the first messenger. When it entered our solar system in October of 2017, it did not follow the same flat plane where the planets circle the Sun. Instead, it came in from above, plunging downward at an astonishing speed of about 87 kilometers every single second. To imagine how fast that is, think of this. In just 1 second, Oumuamua could travel the distance of more than 50 city blocks. That was far too fast for the Sun's gravity to trap it into orbit. Like a skipping stone glancing off the surface of a pond, it simply swung around the Sun and continued on its journey into the deep, dark unknown. But speed was not the only strange thing about Oumuamua. Its movement was irregular. It tumbled and spun in a lopsided way, like a baton thrown into the air. Its shape was also a mystery. Some scientists believed it was long and narrow, stretched out like a giant cigar drifting through space. Others argued it was wide and flat, shaped more like a pancake or a shard of broken glass. And then came the most puzzling detail of all. As Oumuamua left the Sun, it appeared to accelerate slightly, as if something were giving it an extra push. Normally, comets speed up in this way because their icy surfaces heat up near the Sun, releasing jets of gas that act like small thrusters. But telescopes found no visible tail, no cloud of gas, and no signs of outgassing at all. This led to endless debates. Was Oumuamua made of an unusual kind of ice, one that evaporated invisibly? Could it have been a fragment of a shattered planet or moon, hurled across the galaxy in some ancient catastrophe? Or was it something even stranger, a piece of ultra-thin material, perhaps a natural sheet of cosmic foil, being pushed by sunlight like a solar sail? That last idea captured the public imagination. A few respected scientists even suggested that Oumuamua might not be natural at all. Perhaps it was a piece of alien technology, some long-abandoned fragment drifting through space. Most experts disagreed, insisting that it was far more likely to be natural, but the fact that such a possibility was even discussed showed how extraordinary Oumuamua truly was. If Oumuamua was quiet, puzzling and mysterious, Borisov was the opposite. Discovered in August of 2019, It looked exactly like what most people picture when they hear the word comet. It had a bright glowing head and a long streaming tail made of dust and gas. But Borisov's path through the solar system was hyperbolic, meaning it was not bound to the sun and would never return. It too was travelling at enormous speed, more than 30 kilometres every second, clear proof that it had come from another star system. Because Borisov behaved so much like comets we already knew, scientists were able to study it in much greater detail than they could with Oumuamua, and what they found was fascinating. Borisov was similar to our solar system's comets, but not identical. Its dust contained particles that were smaller and more compact than those of most local comets. This suggested that Borisov had formed in a region that was colder or denser than the birthplace of our own solar system. In other words, Borisov carried the fingerprints of another world. It was shaped not by our sun, but by another star, another swirling disk of gas and dust, perhaps another set of planets we will never see. The fact that both Oumuamua and Borisov appeared within 2 short years shook the scientific community. For centuries, astronomers had imagined the space beyond the Oort Cloud as an almost infinite emptiness. Now, evidence suggested it might be a crowded ocean, filled with countless travellers, rocks, comets, shards of planets, and maybe even tiny worlds, slowly drifting from star to star. These wanderers may have been expelled from their birth systems by violent events. Perhaps giant planets slingshot them away, or perhaps they were thrown out during the chaotic births or deaths of stars. Once freed, they would drift through the galaxy for millions or even billions of years, silent and dark, until by chance they crossed paths with another sun, like ours. It is even possible that some of these wanderers have been captured by our sun in the distant past, joining the icy ranks of the Oort Cloud so seamlessly that we can no longer tell which comets are truly ours and which are ancient immigrants from distant suns. If so, then the Oort Cloud is not simply the edge of our solar system. It may be a grand mixing zone where the debris of countless star systems mingle together in a cosmic dance. Until recently, our telescopes were not powerful enough to detect such faint and fast-moving visitors. Oumuamua and Borisov may not have been the first interstellar objects to pass by us, only the first we had the technology to spot. Today, with instruments like Pan-STARRS in Hawaii and the soon-to-be operational Vera Rubin Observatory in Chile, astronomers can scan wide sections of the sky much faster than ever before. This means our chances of finding more interstellar wanderers are growing rapidly.